The Triangulum Galaxy is one of the closest spiral galaxies to the Milky Way and one of the most frequently observed extragalactic systems in modern astronomy. For decades, it was treated as a comparatively simple object, smaller than Andromeda, lacking a dominant central bulge, and assumed to be evolving quietly on the outskirts of the local group. Its proximity made it a convenient laboratory for studying star formation in spiral galaxies, without the complications associated with larger, more massive systems. That assessment changed when the James Webb Space Telescope began returning high-resolution infrared observations. By revealing structures, motions, and material distributions previously hidden by dust, Webb forced a re-evaluation of Triangulum's physical state. What emerged was not a stable, isolated spiral, but a system showing signs of external influence, internal imbalance, and long-term vulnerability. Triangulum in the local group. The Triangulum Galaxy, also catalogued as M33, is located approximately 2.7 million light-years from Earth. It is the third largest member of the local group, after the Milky Way and Andromeda. With a diameter of roughly 60,000 light-years, it is significantly smaller than both of its massive neighbors, yet it remains a fully developed spiral galaxy with well-defined arms, ongoing star formation, and a substantial disk of gas and dust. Triangulum's mass is estimated to be between 10 and 50 billion solar masses, depending on how its dark matter halo is modeled. By comparison, the Milky Way exceeds 1 trillion solar masses when dark matter is included. This difference in scale is central to understanding Triangulum's role within the local group. Gravity governs interactions between galaxies, and in a system dominated by two large spirals, smaller members do not evolve in isolation. Historically, Triangulum was considered a satellite or near satellite of Andromeda, though its exact orbital status remains a subject of ongoing study. Measurements of its velocity relative to both the Milky Way and Andromeda indicate that it is gravitationally influenced by Andromeda's massive halo. Whether Triangulum is on a long-term bound orbit, a highly elliptical trajectory, or a transient pass remains uncertain. But what is clear is that it is not dynamically independent. Triangulum is visible to the naked eye under very dark skies, appearing as a faint smudge in the constellation Triangulum. This visibility is due not to brightness alone, but to proximity. In intrinsic luminosity, it is far less powerful than Andromeda. Its stellar population is dominated by younger stars, and its disk contains a relatively high fraction of gas compared to its total mass. This gas richness made Triangulum an important reference point for studying how stars form in spiral galaxies without the complicating effects of intense central black hole activity. Unlike the Milky Way and Andromeda, Triangulum lacks a prominent central bulge. Its core is diffuse, with no confirmed supermassive black hole. Observations over several decades have placed increasingly strict upper limits on any central black hole mass, suggesting that if one exists, it is several orders of magnitude smaller than those found in larger spirals. This absence has major implications for how energy, gas, and momentum move through the galaxy. The galaxy's spiral arms are loosely wound and asymmetric. Optical observations show numerous star-forming regions scattered across the disk, particularly in the outer arms. These regions contain massive young stars, emission nebulae, and clusters formed within the last few million years. Prior to infrared observations, much of this activity appeared patchy and uneven, reinforcing the idea that Triangulum was a low-efficiency star-forming system. Triangulum also possesses a dark matter halo that extends far beyond its visible disk. This halo provides most of the gravitational binding that holds the galaxy together. However, the halo's mass and shape are still debated. Some models suggest it is less concentrated than those of larger spirals, which would make Triangulum more susceptible to tidal distortion when interacting with nearby massive galaxies. In the context of the local group, Triangulum occupies an intermediate and precarious position. It is too large to be classified as a dwarf galaxy, yet too small to dominate its environment. It exists in the gravitational overlap zone between the Milky Way and Andromeda, where long-term stability is not guaranteed. For much of the 20th century, this positioning was acknowledged but not considered immediately significant. The arrival of detailed infrared data changed that perception. When Triangulum is examined not as a static image, but as a dynamic system of gas flows, stellar populations, and gravitational interactions, its status becomes less secure. Its proximity to Andromeda is not a background detail, but a defining condition. Triangulum's location within the local group places it on a trajectory shaped by forces far larger than itself, and those forces are now visible in ways they were not before. Why Triangulum was considered a simple galaxy? For most of the modern era of astronomy, Triangulum was classified as a comparatively uncomplicated spiral galaxy. This classification did not arise from neglect, but from decades of careful observation using optical and radio telescopes. Compared to the Milky Way and Andromeda, Triangulum appeared smaller, more orderly, and less dynamically active. Its disk showed clear spiral structure without the heavy distortions associated with recent major mergers. Its central region lacked a dense bulge, and no strong evidence pointed to energetic processes at its core. One of the primary reasons for this assessment was the apparent absence of a supermassive black hole. In large spiral galaxies, the presence of a central black hole often dominates the behavior of gas and stars in the inner regions. High-energy radiation, jets, and strong feedback effects can dramatically reshape galactic structure. Triangulum showed none of these signatures. X-ray surveys detected no persistent energetic source at its center, and stellar motion studies failed to reveal the gravitational influence of a massive compact object. As a result, Triangulum was treated as a system governed almost entirely by stellar gravity and dark matter, rather than central activity. Another factor was its star formation rate. Optical observations indicated that Triangulum forms stars at a moderate pace, slower than the Milky Way, but steady over long timescales. Star-forming regions were visible in its spiral arms, but they appeared spatially limited and lacked the intense clustering seen in starburst galaxies. This suggested a stable internal gas supply and an absence of strong external triggers, such as recent close encounters with massive neighbors. Triangulum's rotation curve also reinforced the perception of simplicity. Measurements of how stars and gas move through the disk showed relatively smooth rotational motion. While the presence of dark matter was required to explain the observed velocities, the inferred halo appeared less massive and less centrally concentrated than those of larger spirals. This supported the idea that Triangulum had avoided the violent merger history experienced by many galaxies of comparable age. The galaxy's isolation was another assumption that shaped its reputation. Although its proximity to Andromeda was well known, early models placed Triangulum on a wide, slow orbit with minimal interaction. Without clear tidal tails, stellar streams, or dramatic warping visible in optical light, there seemed to be little evidence that external gravitational forces were actively reshaping the system. In contrast to dwarf galaxies that show obvious signs of stripping and deformation, Triangulum retained a recognizable spiral form. Observational limitations played a crucial role in reinforcing this view. Optical telescopes are sensitive to starlight, but struggle to see through dust. Regions rich in cold gas and embedded star formation often appear dark or empty in visible wavelengths. Radio observations map neutral hydrogen, but lack the resolution to trace fine-scale dynamics across the entire disk. As a result, much of Triangulum's internal structure remained unresolved. This combination of factors led to a working model in which Triangulum was treated as a baseline spiral galaxy. It was used as a reference for studying star formation efficiency, disk stability, and chemical evolution in systems without strong central feedback. In many studies, it served as a control case against which more disturbed or massive galaxies were compared. However, this simplicity was partly an illusion created by the limits of observational tools. The absence of dramatic features in visible light did not mean those features did not exist. It meant they were hidden. dust obscured large fractions of the disk. Cold molecular gas, the raw material for future star formation, was difficult to trace in detail. Subtle distortions in stellar orbits were averaged out in low-resolution measurements. The arrival of infrared observations forced a reassessment of these assumptions. Structures that appeared smooth in optical light began to show asymmetry. Gas distributions that seemed stable revealed signs of motion inconsistent with long-term equilibrium. Regions once thought inactive displayed embedded activity. What had been described as a simple galaxy was revealed to be a system whose apparent calm depended heavily on where and how it was observed. This shift did not invalidate earlier work, but it reframed it. Triangulum was not misclassified due to error, but due to incomplete information. As new instruments expanded the range of observable phenomena, the definition of simplicity itself had to be reconsidered. The galaxy had not changed. The way it could be examined had. In this context, Triangulum's reputation as a quiet, orderly spiral became a starting point rather than a conclusion. The assumption of stability provided a contrast that made later discoveries more significant. Once infrared data exposed the components that optical surveys missed, it became clear that Triangulum's evolutionary path was more complex and more fragile than previously believed. That realization set the stage for a deeper investigation. To understand what Triangulum truly is and what it is becoming required moving beyond visible light entirely. It required observing the galaxy in wavelengths that could trace heat, dust, and motion simultaneously. That capability arrived with a new class of telescope, designed specifically to reveal what had always been there but could not be seen. What the James Webb Space Telescope was designed to see. The limitations that shaped earlier interpretations of Triangulum were not theoretical, but technological. Optical telescopes observed the universe in wavelengths similar to those detected by the human eye. While this approach is effective for mapping bright stars and large-scale structure, it fails in regions dominated by dust, cold gas, and embedded activity. Much of a galaxy's mass and ongoing evolution takes place in precisely those obscured environments. The James Webb Space Telescope was designed to address this gap directly. The James Webb Space Telescope operates primarily in the infrared portion of the electromagnetic spectrum. Infrared light has longer wavelengths than visible light, allowing it to pass through dust that would otherwise block or scatter optical photons. In galactic terms, this means regions that appear dark or empty in visible images can be examined in detail. Dust does not disappear in infrared observations. Instead, it often becomes luminous, emitting thermal radiation that reveals its temperature, density, and distribution. Webb's mirror, measuring 6.5 meters in diameter, was engineered to collect faint infrared signals from distant and cold objects. This large collecting area provides both sensitivity and resolution, allowing astronomers to distinguish fine structural details within nearby galaxies. For Triangulum, this meant resolving individual star-forming regions, tracing gas flows across spiral arms, and detecting subtle distortions that were previously averaged out. Two of Webb's instruments are particularly relevant for galactic studies. The Near-Infrared Camera, or NIRCam, observes wavelengths that capture light from young stars, older red stars, and warm dust. It provides sharp images that can resolve stellar populations across a galaxy's disk. The Mid-Infrared instrument, known as MIRI, operates at longer wavelengths, detecting cooler dust, molecular clouds, and the thermal emission from material heated by star formation or other energetic processes. Together, these instruments offer a layered view of a galaxy's internal structure. Infrared spectroscopy is another critical capability. By splitting infrared light into its component wavelengths, Webb can identify specific molecules and elements within gas clouds. Each molecule absorbs and emits light at characteristic wavelengths, creating distinct spectral signatures. This allows astronomers to determine chemical composition, temperature, and motion. When applied to a galaxy like Triangulum, spectroscopy reveals where gas is cooling, where it is heating, and how it is moving relative to the rest of the system. Webb was also designed to detect faint contrasts in brightness and temperature. In optical images, large-scale features often dominate, masking subtle variations. Infrared data can highlight small but significant differences, such as localized heating from newly formed stars or shock fronts created by gravitational disturbances. These contrasts are essential for identifying processes that indicate instability rather than equilibrium. Another important design feature is Webb's ability to observe continuously without atmospheric interference. Ground-based infrared observations are heavily affected by Earth's atmosphere, which absorbs and emits infrared radiation. Webb operates far from Earth, at the second Lagrange point, where it can maintain a stable temperature and observe without atmospheric noise. This stability allows long exposures and consistent measurements across wide regions of a galaxy. For Triangulum, these capabilities meant that Webb was not simply providing sharper images. It was accessing physical regimes that had never been systematically studied in that galaxy. Cold molecular gas, which forms the raw material for future stars, emits weakly in infrared wavelengths that Webb can detect. Embedded star-forming regions, invisible in optical surveys, become visible as warm knots within dust clouds. Gas flows that subtly deviate from circular motion can be measured through Doppler shifts in spectral lines. Webb was not designed to search for dramatic events alone. Its purpose includes mapping quiet processes that shape galaxies over long timescales. This makes it particularly suited to systems like Triangulum, where change occurs gradually rather than explosively. By observing the distribution and motion of material across the disk, Webb provides data that can be compared directly to theoretical models of galactic stability and evolution. The expectation prior to Webb's observations was that Triangulum would largely confirm existing models. Infrared data were anticipated to fill in missing details, not overturn fundamental assumptions. The galaxy was expected to show hidden star formation, but within the bounds of a stable spiral system. Instead, the data began to suggest a more complex picture, one in which internal processes and external influences intersect. Understanding what Webb was built to see is essential to interpreting what it found. The telescope does not introduce instability into a system, it reveals it. By removing the obscuring effects of dust and providing precise measurements of gas and stars, Webb exposes whether a galaxy is in equilibrium or in transition. In the case of Triangulum, the observations raised questions that could not be answered by optical data alone. With this new observational framework in place, Triangulum could no longer be treated as a static reference object. It became a test case for how smaller spiral galaxies behave when embedded in the gravitational environment of larger neighbors. The next step was to examine what Webb actually observed when it turned its instruments toward Triangulum's disk and began mapping its hidden structure in detail. JWST's first deep infrared maps of Triangulum. When the first deep infrared maps of the Triangulum Galaxy were assembled, they did not present a dramatic single moment of discovery. Instead, they revealed a pattern that emerged gradually as multiple datasets were layered together. The images covered large sections of the galactic disk, spanning near-infrared and mid-infrared wavelengths, each highlighting a different physical component of the system. What appeared was not a uniformly structured spiral, but a galaxy with uneven internal organization. In near-infrared observations, the stellar disk appeared far more crowded than optical images suggested. Regions previously assumed to be sparsely populated showed dense concentrations of older, cooler stars. These stars emit weakly in visible light, but strongly in infrared, and their distribution altered estimates of Triangulum's stellar mass. The disk was heavier and more centrally weighted than earlier models had indicated, though still lacking a dominant bulge. Mid-infrared maps shifted attention away from stars and toward dust. The spiral arms, which looked thin and well-defined in optical images, expanded into broad, complex structures. Dust lanes traced the arms with irregular thickness, showing clumps, gaps, and abrupt changes in density. These features were not symmetrically arranged around the galaxy. One side of the disk contained denser, warmer dust structures than the opposite side, a pattern inconsistent with long-term equilibrium. Temperature mapping added another layer. By measuring infrared emission across multiple wavelengths, astronomers could infer dust temperatures throughout the disk. Instead of a smooth gradient from warm inner regions to cooler outer ones, the maps showed pockets of elevated temperature scattered irregularly across the spiral arms. Some of these regions corresponded to known star-forming complexes, but others appeared in locations previously classified as inactive. The outer disk revealed another surprise. Infrared emission extended farther than expected, tracing faint dust and gas structures well beyond the visible spiral arms. These outer regions showed signs of heating and motion that suggested they were not simply passive reservoirs of material. Their structure appeared stretched and asymmetric, as if influenced by forces acting preferentially along one direction. Gas traced through infrared active molecules showed similar irregularities. The distribution of warm molecular gas did not align neatly with the stellar spiral pattern. In some regions, gas concentrations led the spiral arms. In others, they lagged behind. This misalignment suggested that gas was responding to forces other than the gravitational potential of the stellar disk alone. Resolution played a critical role in revealing these effects. Webb's ability to resolve fine structure meant that features spanning just a few tens of light years could be examined individually. What appeared smooth at lower resolution broke down into networks of filaments and knots. These structures indicated active internal motion rather than static placement. Importantly, these maps showed no evidence of a central organizing engine. There was no dominant infrared source at the core comparable to those seen in galaxies with active nuclei. Instead, energy input appeared distributed across the disk. This decentralization made the observed asymmetries more difficult to explain through internal feedback alone. Comparison with archival optical and radio data highlighted the scale of the discrepancy. Regions that aligned neatly in optical images diverged when examined in infrared. The mismatch suggested that earlier interpretations were biased toward what could be seen rather than what was physically dominant. Dust and gas, though less visually striking, carried most of the information about the galaxy's current state. The overall picture emerging from the first deep infrared maps was not one of collapse or immediate disruption, but of imbalance. Triangulum appeared to be a system in which material was unevenly distributed, unevenly heated, and unevenly moving. These conditions do not necessarily indicate imminent destruction, but they are inconsistent with the idea of a long-lived isolated spiral evolving quietly over billions of years. These findings reframed subsequent analysis. Instead of asking where star formation occurs, researchers began asking why it was concentrated where it was. Instead of assuming gas followed stellar structure, they examined cases where it clearly did not. The maps did not provide answers on their own, but they narrowed the range of plausible explanations. What the first infrared surveys established was a baseline reality. Triangulum's internal structure is more complex and more uneven than previously understood. The galaxy's appearance depends strongly on wavelength, and when dust and heat are included, the system looks less settled. The next step was to focus on the most conspicuous consequence of these conditions: the star formation activity revealed beneath layers of obscuring material that optical telescopes could not penetrate. Hidden star formation beneath the dust. One of the most consequential results of Webb's infrared observations was the reassessment of star formation across Triangulum's disk. Optical surveys had long identified numerous star-forming regions, primarily through the detection of bright, massive young stars and glowing hydrogen nebulae. These indicators, however, only capture star formation once it has already cleared much of its surrounding dust. Infrared data revealed a much earlier and more obscured phase of the process. Beneath thick layers of dust, Webb detected large populations of embedded young stellar objects. These stars are still in the process of forming, drawing material from dense gas envelopes and circumstellar disks. They emit little visible light, but radiate strongly in infrared wavelengths due to the heat generated by gravitational contraction and early nuclear processes. Their presence indicates active star formation in regions that previously appeared inactive or underdeveloped. The spatial distribution of these embedded regions was uneven. Instead of forming a smooth pattern that mirrored the visible spiral arms, many were concentrated in irregular clusters along certain segments of the disk. Some spiral arms showed intense hidden activity, while others of similar size and structure showed comparatively little. This asymmetry suggested that local conditions, rather than global spiral structure alone, were governing where stars could form. Temperature measurements provided further insight. Dust surrounding newly forming stars was consistently warmer than dust in adjacent regions, even when those regions contained similar amounts of gas. This implied that star formation was occurring in short-lived bursts, rather than at a steady rate. Once initiated, these bursts injected energy into their surroundings, altering the local thermal balance and affecting nearby gas clouds. The infrared data also revealed a significant population of intermediate-age star clusters, partially embedded in dust. These clusters represent a transitional phase between deeply embedded protostars and fully exposed stellar groups. Their abundance indicated that Triangulum has been forming stars continuously over the past several hundred million years, but in a spatially and temporally uneven manner. Gas density played a decisive role. Webb's observations showed that the most active hidden star-forming regions coincided with pockets of unusually dense molecular gas. These pockets were not evenly distributed across the disk. Instead, they appeared compressed along specific arcs and filaments, hinting at external or non-axisymmetric forces acting on the gas. Purely internal processes, such as spiral density waves, struggled to account for the observed concentration patterns. Another notable result was the efficiency of star formation in these hidden regions. In several locations, a higher fraction of available gas was being converted into stars than models predicted for a galaxy of Triangulum's mass. This increased efficiency can accelerate gas depletion locally, reducing the long-term star-forming potential of those regions once the burst subsides. The absence of strong central regulation amplified these effects. In galaxies with active nuclei or massive central bulges, energy feedback can redistribute gas or suppress star formation over large scales. Triangulum lacks such a mechanism. As a result, star formation proceeds largely unchecked on local scales, driven by conditions within individual gas clouds rather than by global self-regulation. Over time, this pattern creates imbalance. Regions experiencing repeated bursts of star formation exhaust their gas reservoirs, while other areas retain cold gas but remain inactive. The galaxy does not evolve uniformly. Instead, it develops zones of accelerated aging alongside zones of relative dormancy. Infrared observations made this patchwork evolution visible for the first time. This hidden activity also alters interpretations of Triangulum's past. The presence of numerous intermediate-age clusters embedded in dust suggests that similar bursts likely occurred before, leaving behind stellar populations that optical surveys undercounted. The galaxy's star formation history is therefore more episodic and uneven than previously reconstructed. The significance of these findings extends beyond counting new stars. Star formation reshapes a galaxy's structure by injecting energy, driving turbulence, and redistributing material. In a system as modestly bound as Triangulum, these effects can have lasting consequences. Repeated localized bursts can weaken the coherence of the disk, making it more susceptible to distortion by external gravitational forces. What Webb revealed beneath the dust was not simply more star formation, but a different mode of star formation. It was less orderly, less evenly distributed, and more tightly coupled to dense, unstable gas structures. This raised a critical question. If star formation was behaving this way, What conditions in the surrounding gas were enabling it? Answering that required examining the raw material itself, the cold molecular gas reservoirs that Webb had now brought into view. Unexpected concentration of cold molecular gas. The discovery of extensive hidden star formation immediately redirected attention to the material that makes such activity possible. Stars do not form spontaneously or uniformly across a galaxy. They require cold, dense molecular gas capable of collapsing under its own gravity. Prior to infrared observations, Triangulum was thought to contain a relatively modest and evenly distributed supply of such gas. Webb's data showed that assumption to be incomplete. Infrared observations revealed large reservoirs of cold molecular material embedded deep within the disk. These reservoirs were not faint extensions of known gas clouds, but substantial structures with masses comparable to those found in larger spiral galaxies. Their presence altered estimates of Triangulum's total gas budget and challenged models that treated it as gas-poor relative to its size. The most striking aspect was how this gas was distributed. Instead of forming a smooth disk aligned with the stellar spiral arms, the cold molecular gas appeared concentrated into irregular complexes. These complexes varied widely in size and density, ranging from compact knots tens of light years across to extended filaments stretching hundreds of light years. The pattern lacked the symmetry expected in a stable, long-lived spiral system. Temperature measurements confirmed that these regions were cold by galactic standards, often only a few tens of degrees above absolute zero. Such low temperatures allow molecules to persist and enable gravity to overcome internal pressure. However, the coexistence of extremely cold gas alongside warmer dust and active star formation suggested a dynamic environment in which gas was rapidly cycling between states. The locations of these gas concentrations were not random. Many were positioned along distorted segments of the spiral arms or in regions where the arms appeared broadened or warped. In several cases, dense gas complexes were offset from the visible stellar arms, implying that gas motion was decoupled from stellar motion. This offset is difficult to reconcile with models in which spiral density waves alone govern gas behavior. Spectroscopic data provided additional clues. Molecular emission lines indicated internal motions within these gas clouds that exceeded what would be expected from thermal pressure alone. Turbulence levels were high, suggesting recent compression or ongoing disturbance. In some regions, velocity gradients implied that gas was being funneled or stretched rather than rotating smoothly with the disk. The sheer concentration of cold gas in localized regions raised questions about its origin. One possibility is that Triangulum has been accumulating gas over time from its surroundings, either from the intergalactic medium or through interactions with nearby structures. Another is that existing gas has been redistributed internally by gravitational forces acting unevenly across the disk. What made these findings particularly significant was the absence of a strong stabilizing influence. In more massive galaxies, central bulges and black holes contribute to overall gravitational coherence, helping to regulate how gas settles and flows. Triangulum lacks both. Its gravitational potential is dominated by its disk and dark matter halo, making it more responsive to perturbations. This responsiveness means that even modest external influences can have amplified effects. A weak tidal interaction or a passing disturbance can compress gas in some regions while rarefying it in others. Over time, this leads to the uneven gas distribution now observed. Webb's infrared sensitivity allowed these patterns to be identified directly rather than inferred indirectly. The concentration of cold molecular gas also has implications for Triangulum's future. Gas concentrated into dense pockets is rapidly consumed by star formation. Once exhausted, those regions are unlikely to be replenished quickly, especially if gas inflow is limited or disrupted. This process creates a patchwork disk in which some areas age rapidly, while others remain gas-rich but inactive. These gas reservoirs also represent structural vulnerability. Dense clouds add mass locally, altering gravitational balance and potentially destabilizing surrounding regions. In a galaxy already subject to external gravitational fields, such imbalances can contribute to disk warping and long-term deformation. What Webb revealed was not simply that Triangulum contains more cold gas than expected, but that this gas is organized in a way that suggests ongoing stress. The galaxy is not gently converting a uniform gas supply into stars. It is reacting to uneven forces that concentrate material, trigger bursts of activity, and leave behind depleted regions. Understanding how this gas moves became the next critical step. Static maps could show where material was located, but not how it was behaving over time. To assess whether Triangulum was settling into a new configuration or drifting further from equilibrium required examining the motion of this gas in detail, and that motion told a more unsettling story. Gas motions that do not match stable spiral models. Mapping where gas exists inside Triangulum answered only part of the problem. The more decisive question concerned how that gas was moving. In a stable spiral galaxy, gas follows relatively predictable paths. It orbits the galactic center in near-circular motion, with mild deviations caused by spiral density waves, local turbulence, and star formation feedback. Over long timescales, these motions average out, preserving the disk's overall structure. Webb's infrared spectroscopy showed that Triangulum does not fully conform to this pattern. By analyzing Doppler shifts in infrared emission lines, astronomers were able to measure the velocities of gas clouds across large portions of the disk. These measurements revealed systematic deviations from the smooth rotational curves expected for a galaxy of Triangulum's size and mass. In multiple regions, gas was moving faster or slower than the surrounding stellar population, indicating partial decoupling between stars and gas. One of the most striking features was the presence of radial gas motions. Instead of moving purely around the galactic center, significant amounts of gas were detected flowing inward or outward along the plane of the disk. These radial components were not uniform. Some regions showed inflow toward the inner disk, while others exhibited outward motion away from the core. In stable spiral models, such large-scale radial flows are weak and transient. In Triangulum, they appeared persistent across tens of thousands of light-years. The magnitude of these motions was not extreme by cosmic standards, but it was sufficient to matter. Velocity deviations of even a few tens of kilometers per second can redistribute gas over relatively short astronomical timescales. Over a few 100 million years, such flows can significantly alter where star formation occurs and how mass is distributed within the galaxy. The spatial pattern of these motions was irregular. Gas inflow was not concentrated symmetrically around the center, but instead followed distorted arcs that cut across spiral arm segments. In some cases, inflowing gas appeared to intersect regions of intense star formation, suggesting that compression from converging flows might be triggering bursts of stellar birth. In other regions, gas appeared to be pulled away from star-forming zones, leaving behind depleted areas. These motions challenged the assumption that spiral density waves alone were shaping Triangulum's gas dynamics. Density wave theory predicts that gas should slow slightly as it enters a spiral arm, compress, form stars, and then accelerate as it exits. While some regions fit this pattern, many did not. Gas velocities frequently showed offsets relative to the stellar spiral pattern that could not be explained by internal disk processes alone. Webb's data also revealed shear within gas clouds. Adjacent regions of the same molecular complex were sometimes moving at noticeably different velocities. This internal velocity dispersion exceeded what would be expected from thermal motion or star formation feedback alone. Such shear suggests external stress acting on the gas, stretching and distorting clouds, rather than allowing them to settle into equilibrium. Vertical motions added another layer of complexity. In several areas, gas appeared to be moving slightly above or below the plane of the disk. These vertical excursions were subtle but consistent across multiple observations. In galaxies experiencing tidal interactions, vertical heating of the disk is a common signature. Gas and stars are pulled out of the plane by gravitational forces, thickening the disk and weakening its coherence. The lack of a massive central stabilizing structure amplified these effects. In galaxies with large bulges or central black holes, gravitational potential wells help anchor gas orbits, damping large-scale deviations. Triangulum's shallow central potential offers less resistance to perturbations. As a result, once gas motion becomes distorted, it can persist rather than being quickly smoothed out. Comparisons with numerical simulations provided context. Models of isolated spiral galaxies rarely produce the combination of radial flows, shear, and vertical motion observed in Triangulum without invoking external influence. In contrast, simulations of galaxies subjected to tidal forces from a more massive neighbor often show similar patterns. Gas responds first, due to its dissipative nature, revealing interaction signatures before stars do. The directionality of the gas motions was also telling. When velocities were mapped relative to Triangulum's position in the local group, asymmetries aligned broadly with the direction of Andromeda. Gas on the side of the disk facing Andromeda showed different kinematic behavior than gas on the opposite side. While this correlation does not prove causation on its own, it is consistent with tidal influence acting preferentially along that axis. Another important observation concerned angular momentum. Gas clouds in several regions appeared to be losing angular momentum over time, drifting inward toward the central disk. Angular momentum loss is a prerequisite for gas inflow, but it typically requires torques generated by strong bars or interactions. Triangulum does not possess a prominent bar structure, leaving external gravitational torques as a plausible explanation. These inflows have consequences beyond redistribution. Gas moving inward becomes denser as it enters regions of higher gravitational pressure. This increases the likelihood of collapse and star formation. However, if inflow is uneven, it can create localized starbursts rather than a coherent central buildup. Over time, this leads to structural imbalance rather than orderly growth. Outflows were also detected, though they were weaker and more localized. In regions of recent star formation, gas showed signs of being pushed outward by stellar winds and supernova activity. These feedback-driven motions are expected, but in Triangulum they interacted with larger-scale flows rather than dissipating cleanly. Outflowing gas sometimes collided with inflowing material, creating turbulent interfaces visible in infrared temperature maps. The net result of these complex motions is a disk that is constantly being rearranged. Gas is not simply orbiting and gradually forming stars. It is being shifted, compressed, stretched, and redistributed in patterns that evolve on timescales shorter than the age of the galaxy. This dynamic state undermines the assumption that Triangulum's spiral structure reflects long-term equilibrium. Importantly, these observations do not indicate imminent collapse. The galaxy is not tearing itself apart on human timescales. Instead, they point to gradual erosion of stability. Over hundreds of millions to billions of years, persistent non-circular motions can weaken spiral arms, thicken the disk, and redistribute mass in ways that make the galaxy more susceptible to future disturbances. This behavior also affects how Triangulum interacts with its environment. A galaxy with a dynamically cold, well-ordered disk responds differently to external forces than one already internally stressed. In the latter case, even modest tidal interactions can have outsized effects. Webb's data suggest that Triangulum falls into this second category. What emerged from the kinematic analysis was a picture of a galaxy no longer governed solely by its internal structure. Gas, the most responsive component of the system, was behaving as if influenced by forces acting across scales larger than the disk itself. The patterns were inconsistent with isolation and stability, and they could not be dismissed as transient noise. Understanding the source of these motions became unavoidable. If Triangulum's gas was not following stable spiral dynamics, something had to be exerting sustained influence. Identifying that influence required shifting focus away from internal processes and toward Triangulum's gravitational environment, particularly its relationship with more massive neighbors and the tidal forces they exert. Evidence of external gravitational disturbance. Once internal gas motions were shown to deviate from stable spiral behavior, attention shifted to forces acting beyond Triangulum itself. Galaxies do not exist in isolation, especially within compact groups. Gravity from nearby massive systems can distort structure, alter motion, and redirect material without producing dramatic visual signatures in optical light. Infrared observations made it possible to assess whether such external influences were affecting Triangulum. One of the clearest indicators was large-scale asymmetry in the disk. When the galaxy was examined in infrared wavelengths sensitive to dust and older stars, the disk did not display mirror symmetry across its central axis. One side of the disk appeared more extended, thicker, and structurally complex than the other. This imbalance persisted across multiple wavelengths, ruling out observational artifacts or localized star formation as the cause. The outer disk showed particularly telling features. Infrared emission traced dust and gas farther from the galactic center than optical images had suggested. In these outer regions, material appeared stretched and unevenly distributed. Instead of forming a smooth circular envelope around the galaxy, the outer disk showed elongation along a preferred direction. Such elongation is a common outcome when a galaxy experiences sustained tidal stress. Tidal forces arise when gravitational attraction varies across an object's extent. In the case of Triangulum, the side of the galaxy facing a more massive neighbor experiences a slightly stronger pull than the far side. Over time, this differential force can stretch the disk, distort orbits, and redistribute material. The effects are subtle at first, especially in systems that are still largely intact, but they accumulate. Infrared mapping revealed that Triangulum's stellar distribution was not uniformly affected. Older stellar populations showed mild displacement relative to the galaxy's nominal center, while younger stars remained more tightly clustered within spiral arms. This pattern is consistent with external disturbance acting over long timescales. Older stars, having completed many orbits, integrate the cumulative effects of gravitational stress. Younger stars, formed more recently from gas already responding to those forces, reflect a more localized and transient structure. Gas responded more dramatically. Cold molecular material, already shown to be unevenly distributed, exhibited spatial alignment with the disk's elongation. Dense gas complexes were preferentially located along the stretched axis, suggesting compression driven by external gravitational influence. This compression can trigger star formation, but it also accelerates gas consumption and enhances internal imbalance. The lack of sharp tidal tails does not negate this interpretation. Strong, visually obvious tidal tails typically form during close encounters or mergers. Triangulum's interaction appears to be more gradual and long-term. In such cases, material is distorted and redistributed without being violently expelled. The result is warping, thickening, and asymmetry rather than clear tails. Vertical structure provided additional evidence. Infrared observations detected a slight increase in disk thickness in regions aligned with the elongation. Gas and dust extended farther above and below the galactic plane in these areas than elsewhere. Vertical heating is a known consequence of tidal interaction, as gravitational perturbations inject energy into orbital motion perpendicular to the disk. Another clue came from the relative alignment of different galactic components. In a stable, isolated spiral, the centers of mass traced by stars, gas, and dust coincide closely. In Triangulum, these centers showed small but measurable offsets. The stellar mass distribution, gas concentration, and dust emission peaks did not align perfectly. Such offsets are difficult to maintain without ongoing disturbance, as internal gravitational forces tend to recenter components over time. Velocity field analysis reinforced this picture. Regions showing the greatest structural distortion also exhibited the strongest deviations from circular motion. This correlation suggests a common cause. If internal processes such as star formation feedback were responsible, velocity deviations would be localized around star-forming regions rather than aligned across large-scale structures. The directionality of the disturbance was not random. When mapped in 3 dimensions relative to the local group, the elongation and kinematic asymmetries broadly pointed toward the region of space dominated by a more massive neighbor. This alignment supports the interpretation that Triangulum's evolution is being shaped by its environment rather than by isolated internal processes. Time plays a critical role in interpreting these observations. Tidal effects do not require a single dramatic event. Even a modest gravitational influence, if applied continuously over billions of years, can reshape a galaxy. Triangulum's mass places it in a vulnerable category. It is massive enough to retain a spiral form for long periods, but not massive enough to fully resist external perturbations. Numerical models of similar systems help contextualize the observations. Simulations of small spiral galaxies orbiting larger hosts often show initial stages that closely resemble Triangulum's current state. The disk becomes asymmetric, gas redistributes unevenly, star formation becomes patchy. The galaxy remains visually recognizable as a spiral, but its long-term stability is compromised. These models also show that the earliest and most sensitive indicators of disturbance appear in gas and dust, precisely the components Webb is best suited to observe. Stars, especially older populations, respond more slowly. By the time stellar streams or pronounced warping become obvious in optical light, the underlying process has often been underway for a long time. Triangulum's apparent calm in visible wavelengths therefore becomes misleading. The absence of obvious disruption does not imply isolation. Infrared data reveal that the galaxy is already responding dynamically to external forces, even if its overall shape remains intact. Importantly, this interpretation does not rely on any single observation. It emerges from the convergence of multiple lines of evidence: asymmetric structure, uneven gas concentration, vertical thickening, kinematic distortion, and component misalignment. Each on its own might be ambiguous. Together, they form a coherent picture of external gravitational disturbance. This disturbance does not dictate a single outcome. Galaxies subjected to tidal influence can survive for long periods, gradually losing mass or reshaping their structure without immediate destruction. However, once a system enters this state, its evolution diverges from that of an isolated galaxy. Its future becomes tied to the dynamics of its environment. For Triangulum, this raises a broader question. If external gravitational forces are already influencing its structure and motion, what is the nature of its long-term relationship with the dominant mass in its vicinity? Understanding that relationship requires examining Triangulum not as an independent object, but as part of a larger gravitational system whose dynamics extend well beyond its visible disk. Triangulum's relationship with Andromeda revisited. Understanding whether Triangulum's observed disturbances originate internally or externally requires placing the galaxy within its full gravitational context. That context is dominated by Andromeda, the most massive member of the local group. For much of the 20th century, the relationship between Triangulum and Andromeda was treated as loosely connected but dynamically unimportant. Webb-era data, combined with improved kinematic measurements, have forced a reassessment of that assumption. Triangulum lies at a projected distance of roughly 750,000 light-years from Andromeda. In galactic terms, this separation is not large. Andromeda's dark matter halo is believed to extend well beyond its visible disk, possibly exceeding 1 million light-years in radius. This means Triangulum exists within, or at least on the boundary of, Andromeda's extended gravitational influence. The question is not whether Andromeda affects Triangulum, but how strongly and in what manner. Early models of Triangulum's orbit relied on limited velocity data. Radial velocity measurements showed that Triangulum was moving relative to both Andromeda and the Milky Way, but without accurate proper motion data, its three-dimensional trajectory remained uncertain. As a result, astronomers often assumed a wide, slow orbit that minimized interaction. This assumption allowed Triangulum to be treated as an effectively isolated system for many analytical purposes. That picture began to change as more precise measurements became available. Observations using radio interferometry and long baseline astrometry refined estimates of Triangulum's motion through space. These data suggested that Triangulum's velocity relative to Andromeda was lower than expected for a completely unbound object. Instead, its motion appeared consistent with a system that has experienced prolonged gravitational interaction. One critical factor is mass ratio. Andromeda is several tens of times more massive than Triangulum when dark matter is included. In such unequal pairings, the smaller galaxy's orbit is easily altered by even modest uncertainties in initial conditions. Small changes in velocity or direction can determine whether a satellite remains loosely bound, becomes tightly captured, or gradually spirals inward through dynamical friction. Dynamical friction plays a central role in this relationship. As Triangulum moves through Andromeda's dark matter halo, it gravitationally perturbs the surrounding matter. These perturbations create a trailing wake of enhanced density that exerts a drag force on Triangulum. Over long timescales, this process drains orbital energy and angular momentum, causing the smaller galaxy's orbit to decay. The effect is subtle and slow, but cumulative. The strength of dynamical friction depends on several factors: the mass of Triangulum, the density of Andromeda's halo, and the relative velocity between the two systems. Current estimates place Triangulum in a regime where friction is weak but non-negligible. This suggests that if Triangulum has been orbiting Andromeda for billions of years, its orbit would have evolved measurably over that time. Infrared observations provide indirect support for this scenario. The asymmetries and gas motions observed in Triangulum align with what simulations predict for a satellite experiencing repeated tidal stress near the periphery of a massive halo. These effects do not require close encounters. Even distant passages through denser regions of the halo can generate persistent distortion, particularly in gas-rich, low-mass spirals. Another line of evidence comes from Triangulum's stellar populations. Age and metallicity gradients across the disk are not uniform. Certain regions show stellar compositions consistent with prolonged gas inflow or compression, while others appear relatively quiescent. These patterns are difficult to reconcile with purely internal evolution, but align with scenarios in which external gravitational fields periodically influence gas distribution and star formation. The lack of a dominant central bulge in Triangulum further amplifies Andromeda's influence. Central bulges contribute significantly to a galaxy's overall gravitational stability. Without one, Triangulum relies more heavily on its disk and halo for structural integrity. This makes it more susceptible to tidal heating and disk warping when exposed to external forces. Importantly, Andromeda's influence is not static. The local group itself is evolving. Andromeda and the Milky Way are on a slow collision course, altering the gravitational landscape over time. As these two massive galaxies approach each other, their halos increasingly overlap. Triangulum exists within this evolving overlap region, where gravitational forces are neither simple nor constant. This dynamic environment complicates orbital reconstruction. Triangulum's past trajectory cannot be inferred by assuming a fixed gravitational potential. Instead, its orbit must be modeled within a changing field shaped by the mutual motion of the Milky Way and Andromeda. Recent simulations that incorporate this evolving context tend to produce scenarios in which Triangulum experiences long-term, low-level tidal stress rather than remaining unaffected. Some models suggest that Triangulum may be on its first infall toward Andromeda, having previously existed at a greater distance. Others indicate that it could be a long-term satellite on a wide, eccentric orbit. In both cases, the implications are similar. The galaxy would experience periods of increased tidal influence as it passes through denser regions of Andromeda's halo, interspersed with quieter phases. What Webb's observations add to this discussion is timing. The current state of Triangulum's gas and disk suggests ongoing rather than purely historical disturbance. Gas motions, asymmetry, and star formation patterns point to forces that are active now or have been active in the recent past. This argues against a scenario in which all interaction occurred billions of years ago and has since ceased. The absence of dramatic stellar streams connecting Triangulum and Andromeda has sometimes been cited as evidence against strong interaction. However, stellar streams form most readily during close passages or partial disruption events. If Triangulum's interaction has remained at a moderate distance, gas would respond first and most strongly, while stars would retain a largely coherent distribution. This is consistent with what is observed. Triangulum's position relative to Andromeda's disk also matters. It does not lie in the plane of Andromeda's stellar disk, but rather at an inclined angle. This geometry favors tidal effects that warp and heat the disk of the smaller galaxy, without producing direct collisions between dense stellar components. Gas, being dissipative, absorbs much of this energy, while stars respond more gradually. The relationship between Triangulum and Andromeda is therefore best described as asymmetrical and evolving. Andromeda shapes Triangulum's fate far more than Triangulum affects Andromeda. The smaller galaxy's structure, gas content, and star formation history increasingly reflect this imbalance. This reassessment changes how Triangulum is categorized. It is not merely a nearby spiral observed in isolation. It is a system whose current state is intertwined with the gravitational dominance of a larger neighbor. Its apparent independence is provisional and likely temporary on cosmological timescales. The implications extend beyond Triangulum itself. Many small spiral galaxies observed throughout the universe exist near larger hosts. Triangulum provides a nearby example of how such systems behave when subjected to long-term tidal influence without immediate destruction. It illustrates a mode of galactic evolution that is neither catastrophic nor static, but gradually transformative. As evidence accumulates, the distinction between satellite and independent galaxy becomes less clear-cut. Triangulum occupies an intermediate category, large enough to maintain a spiral form, yet small enough to be shaped by its environment. Webb's observations make that shaping process visible in ways that were not possible before. The next step in understanding Triangulum's trajectory involves examining the direct consequences of this relationship. If Andromeda's gravitational field is influencing Triangulum, then material should not only be redistributed internally, but also removed over time. Detecting whether such removal is occurring requires looking for signs of mass loss rather than mere distortion, and those signs begin to appear when attention turns to the edges of the galaxy's disk. Signs of ongoing tidal stripping. Distortion alone does not confirm mass loss. A galaxy can be warped, heated, or internally rearranged while retaining most of its material. Tidal stripping represents a more advanced stage of interaction, one in which gravitational forces remove gas and stars from a system faster than they can be reaccreted. Determining whether Triangulum is undergoing this process requires examining the outermost regions of its disk, where gravitational binding is weakest and external forces act most efficiently. Infrared observations extended Triangulum's detectable structure well beyond what optical surveys had previously mapped. In these faint outer regions, dust and gas did not form a smooth continuation of the inner disk. Instead, they appeared fragmented and uneven. Emission was patchy, with elongated features that lacked the curvature expected from circular rotation. Such structures are characteristic of material that is no longer fully bound to the galactic disk. Gas provided the clearest evidence. Neutral and molecular gas detected in infrared and radio wavelengths showed decreasing surface density with radius, as expected, but the decline was not uniform. On one side of the galaxy, gas extended farther out, while on the opposite side, it dropped off sharply. This asymmetry is difficult to explain through internal processes alone, which tend to produce radially symmetric profiles when averaged over time. Velocity measurements reinforced this interpretation. Gas in the outer disk exhibited increased velocity dispersion and reduced coherence in rotation. Instead of following well-defined orbits, some clouds appeared to be drifting relative to the disk's overall motion. In gravitational terms, this indicates that these clouds are only marginally bound. A small additional perturbation could remove them entirely. The direction of these irregularities was not random. When mapped relative to Triangulum's orientation within the local group, the regions showing the strongest signs of weakening gravitational binding aligned broadly along the axis toward Andromeda. This alignment supports a scenario in which tidal forces are preferentially acting on the side of the galaxy facing the more massive neighbor. Stripping does not occur uniformly across all components. Gas is affected first because it is less tightly bound than stars and responds dissipatively to external forces. Webb's infrared data revealed extended, low-density gas structures that appear disconnected from the main disk. These structures lack the density required for sustained star formation and show kinematic signatures inconsistent with long-term orbital stability. Stars are more resistant, but even here subtle signs emerge. In the extreme outer regions, older stellar populations appeared more diffuse and less centrally concentrated than expected for an undisturbed spiral. While no prominent stellar streams were detected, the gradual thinning of stellar density suggests that some stars may be transitioning into loosely bound orbits within the surrounding halo rather than remaining confined to the disk. This mode of stripping is consistent with what simulations describe as tidal evaporation rather than tidal disruption. Instead of dramatic tails or bridges, material is slowly peeled away over repeated orbital passages. Each interaction removes a small fraction of mass. Over billions of years, the cumulative effect becomes significant. Another indicator lies in the mismatch between gas loss and star formation history. Regions of the disk that show evidence of recent star formation bursts are often adjacent to areas where gas density has dropped sharply. This spatial relationship suggests that gas compression and star formation are followed by depletion, with little replenishment. If gas were simply cycling internally, these depleted regions would be refilled over time. The lack of such refilling points to net loss. The gravitational potential of Triangulum plays a critical role in determining how stripping proceeds. With a relatively shallow potential well compared to larger spirals, the galaxy relies heavily on its dark matter halo to retain material at large radii. If the halo itself is distorted or truncated by Andromeda's influence, the binding energy of outer gas clouds decreases further. Infrared observations hint at this possibility through asymmetries in how material is distributed around the disk. Environmental factors amplify the effect. The intergalactic medium within the local group is not empty. As Triangulum moves through this medium, ram pressure can act on its gas, especially in the outskirts where densities are low. While ram pressure alone is unlikely to strip large amounts of gas from a galaxy as massive as Triangulum, it can assist tidal forces by removing already weakened material. The combined action of tidal stress and environmental interaction creates a one-way process. Gas removed from the disk is unlikely to return in a form that can support future star formation. Instead, it becomes part of the diffuse medium surrounding the galaxy or is incorporated into the halo of a more massive neighbor. This gradual loss reduces the galaxy's ability to sustain itself over long timescales. The timescales involved are long by human standards, but short in cosmic terms. Simulations suggest that a galaxy like Triangulum could lose a significant fraction of its outer gas over several billion years through such processes. The inner disk may remain intact, continuing to form stars for some time. But the overall system becomes progressively more compact and less gas-rich. This pattern has been observed in other satellite galaxies across the universe. Systems that begin as gas-rich spirals often evolve into gas-poor, quiescent disks or spheroidal remnants after prolonged interaction with larger hosts. Triangulum appears to be in an early to intermediate stage of this transformation. What makes Triangulum distinctive is that this process is occurring without the dramatic signatures typically associated with galactic interaction. There is no ongoing merger, no obvious collision, and no catastrophic disruption. Instead, the galaxy is being altered quietly through persistent, low-level forces that act most strongly where the galaxy is weakest. These observations challenge the notion that a spiral galaxy must experience a major event to lose its identity. In Triangulum's case, identity erosion appears to be incremental. Each episode of gas loss, each redistribution of material, slightly reduces the galaxy's capacity to behave as it once did. The significance of ongoing tidal stripping lies not in its immediacy, but in its directionality. The process does not reverse naturally. Once material is removed, the system's future options narrow. Star formation becomes increasingly centralized and episodic. The outer disk grows inert. Structural coherence weakens. At this stage, Triangulum remains a spiral galaxy in both appearance and classification. However, the evidence suggests it is no longer maintaining itself against its environment. Instead, it is adapting to external gravitational dominance by shedding material it can no longer hold. Understanding the long-term outcome of this process requires examining not just what is being lost, but how the remaining material responds. As stripping progresses, the internal balance between stars, gas, and dark matter changes. That shift alters how the galaxy evolves from within, setting the stage for further structural transformation driven by forces both internal and external. The dark matter halo is not holding. For most of the 20th century, astronomers believed galaxies were defined by what they could see. Stars, gas, dust, and glowing nebulae shaped classification systems and evolutionary theories. That view collapsed once rotation curves revealed a hidden truth. Galaxies are dominated not by visible matter, but by dark matter. For a system like the Triangulum Galaxy, dark matter is not an accessory. It is the scaffold that keeps the galaxy intact. And the most unsettling implication of recent observations is that this scaffold may be compromised. A galaxy's dark matter halo extends far beyond its visible disk. In Triangulum's case, estimates suggest the halo reaches several 100,000 light-years into space, enveloping the spiral arms and providing the gravitational glue that prevents stars and gas from drifting away. If this halo were perfectly spherical and undisturbed, the galaxy would be resilient to external forces. But Webb-supported data, combined with dynamical studies, increasingly suggest that Triangulum's halo is neither spherical nor stable. The first indication comes from rotation behavior. In an isolated galaxy, rotation curves remain flat at large radii because dark matter continues to provide gravitational support, even where visible matter thins out. Triangulum's rotation curve, however, shows irregularities at its outer edge. Instead of remaining smooth and symmetric, velocities fluctuate in ways that cannot be fully explained by internal structure or gas distribution alone. These deviations imply variations in the underlying gravitational potential. Such variations are difficult to reconcile with a pristine halo. They suggest distortions, elongation, or truncation of the dark matter distribution. In practical terms, parts of the halo may be stretched or compressed, reducing its ability to bind material evenly across the disk. This is precisely what would be expected if the halo were experiencing sustained tidal stress from a more massive neighbor. Dark matter does not interact electromagnetically, so Webb cannot observe it directly. Instead, its presence and structure are inferred from how visible matter behaves. When gas clouds accelerate faster than expected, when stellar orbits become asymmetric, or when disk stability varies with direction, Dark matter is the only viable explanation. In Triangulum, these effects are directionally dependent. The strongest anomalies occur along the axis oriented toward Andromeda. Simulations provide a framework for understanding this behavior. When a smaller galaxy orbits within the gravitational influence of a much larger one, its dark matter halo is affected first. Long before stars or gas are stripped, the outer halo begins to deform. Tidal forces stretch it into an elongated shape, pulling dark matter away from the satellite galaxy and redistributing it into the host's halo or the surrounding intergalactic medium. This process is subtle but irreversible. Unlike stars, dark matter does not radiate energy and cannot dissipate heat to settle back into a stable configuration. Once stripped or displaced, it remains dispersed. Over time, the halo becomes less massive, less symmetric, and less capable of anchoring the galaxy's visible components. Evidence that this is already happening in Triangulum comes from mass estimates. Independent measurements using stellar dynamics, gas rotation, and satellite motions yield slightly different total mass values depending on direction and radius. These inconsistencies point to a halo that is no longer uniform. Instead of a smooth gravitational envelope, Triangulum may possess a lopsided or partially truncated halo. The consequences of this are profound. The dark matter halo sets the depth of the gravitational well. As it weakens, the galaxy's escape velocity drops, particularly in the outskirts. Gas clouds that once would have remained bound can now drift away. Stars on wide orbits become vulnerable to tidal heating and gradual evaporation into the surrounding environment. This feeds directly into the stripping processes observed in the previous chapter. Another clue lies in Triangulum's interaction history. Orbital reconstructions suggest the galaxy may have passed relatively close to Andromeda in the past, possibly within a few 100,000 light-years. Such encounters would not necessarily produce dramatic tidal tails, but they would strongly affect the dark matter halo. Each passage would peel away a fraction of the outer halo, leaving the inner regions increasingly exposed. The loss of dark matter also changes how the galaxy responds internally. Spiral structure relies on a delicate balance between disk mass, rotational shear, and gravitational stability. As halo support diminishes, this balance shifts. Spiral arms can weaken, fragment, or become transient features rather than long-lived structures. Webb's infrared images already show spiral arms in Triangulum that are less coherent than expected for a galaxy of its type. Star formation patterns reflect this change. Regions that once formed stars steadily now do so in bursts, triggered by local instabilities rather than global disk dynamics. This transition is characteristic of galaxies whose dark matter halos have been disturbed. Without a stable halo, gas flows become chaotic and star formation loses its regularity. There is also the question of halo overlap. Andromeda's dark matter halo is enormous, likely extending more than 1 million light-years from its center. Triangulum resides well within this envelope. This means the two halos are not merely interacting at their edges, they are interpenetrating. In such a configuration, Triangulum's halo does not exist in isolation. It is embedded within a larger gravitational structure that can siphon dark matter away continuously. This scenario helps explain why Triangulum appears to be losing mass without showing classic merger signatures. The stripping is happening in the dark sector first, invisibly, setting off a chain reaction that only later affects stars and gas. By the time visible disruption becomes obvious, the underlying cause has been operating for billions of years. The terrifying implication is that dark matter loss is a tipping point. Once a galaxy's halo falls below a certain threshold, recovery becomes impossible. Even if external forces weaken temporarily, the galaxy lacks the gravitational depth to reassemble what was lost. From that point forward, evolution proceeds in only one direction, toward reduced mass, diminished star formation, and eventual structural simplification. For Triangulum, this does not mean imminent destruction. The inner halo and disk remain intact, and the galaxy will persist for billions of years. But its fate may already be sealed. Instead of remaining an independent spiral indefinitely, it may be on a slow trajectory toward becoming a stripped, gas-poor remnant orbiting within Andromeda's domain. This raises a broader question about galactic identity. At what point does a galaxy cease to be a self-contained system and become merely a substructure of a larger one? If Triangulum's dark matter halo is being absorbed into Andromeda's, the distinction becomes increasingly blurred. The galaxy may retain its visual form while losing the gravitational independence that defines it dynamically. The situation also reframes the future of the local group. Andromeda is not merely approaching the Milky Way as a future collision partner. It is already exerting dominance over its surroundings, reshaping smaller galaxies long before any direct merger occurs. Triangulum may be the clearest example of this process in action. Dark matter halos were once thought to be passive containers, unaffected by environment unless a violent merger occurred. Triangulum suggests otherwise. Halos can be eroded quietly, gradually, and relentlessly, with consequences that only become visible much later. By the time astronomers detect changes in star formation or disk structure, the real damage has already been done. What makes this unsettling is the timescale. These processes unfold over billions of years, giving the illusion of stability when viewed over short observational windows. Yet when data from multiple wavelengths and methods are combined, a consistent picture emerges. Triangulum is no longer fully supported by its dark matter foundation. This realization forces a reconsideration of how galaxies survive in groups and clusters. Independence is not guaranteed by size alone. It depends on maintaining a halo massive enough to resist external tides. Once that halo begins to fail, the galaxy enters a slow decline that cannot easily be reversed. In the next chapter, this weakening foundation will be traced forward in time. If the dark matter halo continues to erode, how will Triangulum's structure change? What happens to its spiral arms, its star-forming regions, and its long-term role within the local group? The answers point toward a future that is quieter than destruction, but far more final in its implications. Triangulum's orbit is not stable. For decades, Triangulum was described as a companion galaxy, a small spiral moving peacefully alongside Andromeda, loosely bound but structurally independent. That description depended on one critical assumption, that Triangulum followed a stable, long-term orbit. Recent data no longer supports that assumption. Instead, the evidence increasingly indicates that Triangulum's trajectory is evolving in ways that undermine its long-term stability. Orbital stability in galactic systems is not intuitive. Galaxies do not move like planets around a star. They are extended objects with diffuse mass distributions, embedded in overlapping dark matter halos. Their motion is governed not just by gravity between two-point masses, but by continuous tidal interactions, dynamical friction, and the transfer of orbital energy into internal motion. In such systems, an orbit can slowly decay without any dramatic visual signal. Triangulum's motion relative to Andromeda has been measured using a combination of proper motion data and line-of-sight velocities. These measurements are difficult and uncertain, but over the past decade they have improved significantly. When these data are fed into dynamical models, a consistent pattern emerges. Triangulum's orbit is not closed or repeating, it is decaying. One of the clearest indicators comes from velocity anisotropy. If Triangulum were on a long-term stable orbit, its velocity components would align with predictions for a bound, near-circular or mildly elliptical trajectory. Instead, its tangential velocity appears lower than expected. This implies that a significant fraction of its motion is radial, directed inward toward Andromeda rather than sideways around it. Radial dominance is a warning sign. In gravitational systems, objects on highly radial orbits are more susceptible to tidal stripping and orbital decay. Each close approach transfers orbital energy into internal heating. Over time, the orbit shrinks. The object does not simply swing past and return to its previous distance. it loses energy and sinks deeper into the gravitational well. This process is amplified by dynamical friction. As Triangulum moves through Andromeda's dark matter halo, it gravitationally perturbs the surrounding dark matter particles. Those particles form a trailing wake behind the galaxy. The gravitational pull of that wake acts as a drag force, slowing Triangulum down. The more massive the surrounding halo, the stronger this effect becomes. Dynamical friction does not require physical contact. It operates continuously as long as Triangulum moves through Andromeda's halo. Because Andromeda's halo is both massive and extended, Triangulum has likely been experiencing this drag for billions of years. Each orbit loses a small amount of energy. Over cosmic timescales, those losses accumulate. Orbital reconstructions suggest that Triangulum may have already passed through one or more pericentric encounters, periods when it came significantly closer to Andromeda than it is today. These encounters would not necessarily produce dramatic tidal tails, especially if the closest approach remained outside the visible disk, but they would have profound effects on the dark matter halo and orbital energy. The timing of these encounters aligns with other anomalies. Estimates place a close passage within the last few billion years, coinciding with changes in Triangulum's star formation history and the onset of disk asymmetries. While correlation does not prove causation, the consistency across independent datasets strengthens the case. Another destabilizing factor is the three-body environment of the local group. Triangulum does not orbit Andromeda in isolation. The Milky Way exerts its own gravitational influence. While weaker than Andromeda's at Triangulum's current location, it is not negligible. Over long timescales, this influence can alter orbital parameters, injecting chaos into what might otherwise be a predictable trajectory. Simulations that include all three galaxies show a wide range of possible futures for Triangulum. In many scenarios, the orbit becomes increasingly eccentric. In others, Triangulum is eventually captured more tightly by Andromeda and drawn inward. Only a minority of models preserve a stable, long-lived orbit that keeps Triangulum safely distant over the next 10 billion years. What makes the current situation particularly concerning is that orbital decay accelerates once it begins. As Triangulum moves closer, it passes through denser regions of Andromeda's halo. Dynamical friction increases, tidal forces strengthen, the rate of energy loss grows. This creates a feedback loop in which decay feeds on itself. This is not speculation. Similar processes are observed in satellite galaxies throughout the universe. In galaxy clusters, smaller galaxies routinely spiral inward towards central giants, losing mass and orbital energy until they are absorbed. The only difference here is scale and timescale. Triangulum is larger than most satellites, so the process is slower, but the underlying physics is the same. The instability of Triangulum's orbit also explains why its structural disturbances are directional. Features such as disk warping, gas asymmetry, and velocity gradients tend to align with the direction of motion towards Andromeda. These are signatures of repeated tidal stressing along a preferred axis, not random internal evolution. Another subtle indicator lies in Triangulum's angular momentum. A stable orbit would preserve angular momentum over time, aside from minor perturbations. However, models indicate that Triangulum's angular momentum relative to Andromeda is decreasing. This loss must go somewhere. It is transferred into internal heating of Triangulum's disk and into the surrounding dark matter halo. Internal heating manifests as increased velocity dispersion among stars and gas. This is observed. Triangulum's disk is dynamically warmer than expected for a galaxy of its mass. Stars exhibit higher random motions, and gas clouds show elevated turbulence. These effects are consistent with long-term tidal heating rather than recent violent interaction. The implications extend beyond Triangulum itself. If its orbit is unstable, then its future role in the local group is fundamentally different from what was once assumed. Instead of remaining a third major galaxy alongside Andromeda and the Milky Way, it becomes a transitional object. a galaxy in the process of being absorbed, even if that process takes several billion years to complete. This reframes Triangulum's significance. It is no longer just a nearby spiral studied for convenience. It is a live case study in slow galactic capture. Observing it now is equivalent to observing a system midway through a transformation that is usually inferred only from remnants. The instability also introduces uncertainty into predictions of the future Milky Way-Andromeda merger. Triangulum's mass and trajectory affect the dynamics of that event. If Triangulum is drawn inward beforehand, it may merge with Andromeda prior to the Milky Way's arrival. Alternatively, it could be flung onto a radically different orbit during future interactions, becoming a long-lived but heavily stripped remnant. None of these outcomes involve sudden catastrophe. There will be no single moment when Triangulum visibly falls in. The process is gradual, distributed across billions of years, and largely invisible without precise measurements. That is what makes it unsettling. The galaxy can appear intact while its orbit quietly deteriorates. From a human perspective, this instability is imperceptible. Over a lifetime, Triangulum's position in the sky is effectively fixed. Even over centuries, its motion is negligible. Yet on cosmic timescales, it is already drifting toward a different fate than previously assumed. The conclusion that emerges from orbital analysis is not dramatic, but definitive. Triangulum is not on a secure path. Its motion is shaped by forces that steadily reduce its independence. Whether it ultimately merges, is partially stripped and left as a remnant, or survives in a heavily altered state depends on variables still being refined. What is clear is that orbital instability compounds every other vulnerability already identified. A weakened dark matter halo, disrupted gas distribution, and uneven star formation all become more consequential when the galaxy's trajectory itself is changing. Stability in one domain cannot compensate for instability in another. The next question, then, is how this unstable motion manifests within the galaxy's visible structure. If the orbit continues to decay, what happens first? Does the disk thicken, the spiral pattern dissolve, or the gas supply collapse? The answers lie in how orbital instability translates into internal transformation, and that transformation is already underway. The disk is heating and thickening. Galactic disks are fragile structures. Their defining feature is order, stars and gas moving on largely circular orbits within a thin plane. This order is not permanent. It depends on a balance between gravity, rotation, and the stabilizing influence of a dark matter halo. When that balance is disturbed, disks do not tear apart immediately. Instead, they heat up. Disk heating is a technical term. It does not refer to temperature in the everyday sense, but to motion. A cold disk is one in which stars and gas move in orderly, predictable paths with little random motion. A hot disk is one in which those paths become increasingly chaotic. Velocities scatter, orbits tilt. The disk thickens as material moves above and below the galactic plane. In Triangulum, this process is no longer theoretical. Measurements of stellar motion show that its disk is dynamically warmer than expected for a galaxy of its size and morphology. Stars exhibit higher velocity dispersion, meaning their motions deviate more strongly from circular rotation. Gas clouds show elevated turbulence. These are not isolated anomalies. They appear consistently across large portions of the disk. This heating does not arise spontaneously. It requires energy input. In galaxies, that energy comes from gravitational interactions. Tidal forces inject kinetic energy into stellar orbits. Dynamical friction transfers orbital energy into internal motion. Repeated weak encounters can have the same cumulative effect as a single strong one. Triangulum's environment provides all the necessary ingredients. Its orbit through Andromeda's halo subjects it to continuous tidal stress. Each pass through denser regions of the halo perturbs the disk slightly. Each perturbation is small, but none are reversed. Over billions of years, the disk absorbs this energy, and its internal motions grow increasingly disordered. One of the earliest signs of disk heating is vertical thickening. In a cold spiral disk, most stars remain close to the midplane. As random motions increase, stars begin to oscillate farther above and below that plane. The disk becomes thicker, losing its razor-thin profile. Observations indicate that Triangulum's stellar disk is already thicker than predicted by models assuming long-term isolation. This thickening is not uniform. It is more pronounced in the outer disk, where gravitational binding is weakest. That spatial pattern matters. Internal processes such as star formation feedback tend to heat disks from the inside out. Tidal heating works from the outside inward. Triangulum shows the latter signature. Gas responds differently than stars, but it also shows signs of disturbance. Molecular clouds exhibit increased velocity dispersion, meaning they move faster relative to each other than expected. This turbulence inhibits orderly collapse. While some regions still form stars efficiently, others are stabilized against collapse by excess motion. This contributes to the patchy star formation pattern already observed. Heating also disrupts spiral structure. Classic spiral arms rely on coherent orbital motion to maintain their shape. As velocity dispersion increases, those arms lose contrast and continuity. They fragment into segments or dissolve into flocculent patterns. Triangulum's spiral arms appear less defined and more irregular than those of similar isolated spirals. This is not merely an aesthetic change. Spiral arms play a key role in funneling gas and triggering star formation. When they weaken, the galaxy's ability to regulate where and when stars form is compromised. Star formation becomes more stochastic, driven by local conditions rather than global structure. The thickening disk also alters how Triangulum interacts with its surroundings. A thin disk presents a smaller cross-section to tidal forces. A thicker disk is more easily perturbed. As the disk puffs up, it becomes more responsive to external gravitational fields, accelerating the heating process further. This creates another feedback loop. Importantly, disk heating is largely irreversible. Cooling mechanisms exist for gas, which can radiate energy and settle back into a thinner configuration under the right conditions. Stars cannot do this. Once stellar orbits are randomized, there is no mechanism to restore order on galactic scales. The disk's stellar component permanently thickens. This distinction between stars and gas has long-term consequences. Over time, the stellar disk becomes a thick disk, while any remaining gas may form a thinner layer within it. This decoupling changes the galaxy's appearance and evolution. Many lenticular and early-type spiral galaxies show evidence of this transformation, often attributed to environmental effects. Triangulum appears to be moving along that path. It is not yet a thick disk galaxy in the classical sense, but the trend is clear. The ratio of vertical to radial velocity dispersion is increasing. The scale height of the disk is growing. These are measurable quantitative indicators of heating. The heating also affects angular momentum distribution. In a cold disk, angular momentum is neatly organized, with most of it aligned with the disk's rotation axis. As orbits become inclined and eccentric, angular momentum becomes redistributed. Some is transferred outward, some inward, and some lost to the surrounding halo. This redistribution further weakens the disk's structural coherence. Another consequence is increased susceptibility to bar formation. Heated disks can become unstable in new ways. In some cases, they form central bars as angular momentum is redistributed. In others, heating suppresses bar formation entirely by preventing the coherent motion required to sustain one. Triangulum's lack of a strong central bar is consistent with a disk that is dynamically warm, but not yet reorganized into a new stable configuration. Heating also complicates the interpretation of mass measurements. When stars have significant random motion, simple rotation-based estimates of mass become less accurate. Corrections must be applied to account for pressure support. This adds uncertainty to determinations of Triangulum's remaining dark matter content and accelerates debates about how much of its halo has already been lost. The process is gradual enough that it can be mistaken for internal evolution. Without external context, One might attribute disk heating to long-term star formation feedback or minor internal instabilities. But the spatial patterns, kinematic signatures, and alignment with Andromeda-facing directions point strongly toward an external driver. What makes this particularly important is timing. Disk heating tends to accelerate once it begins. As the disk thickens, it couples more strongly to tidal fields. As orbital decay progresses, pericentric passages become more damaging. The system enters a phase where structural change becomes the norm rather than the exception. This does not mean Triangulum will suddenly lose its disk. Many galaxies retain thickened disks for billions of years, but the character of that disk changes. It becomes less efficient at forming stars, less responsive to density waves, and less capable of maintaining long-lived spiral structure. Over time, it begins to resemble the disks seen in galaxies transitioning towards earlier morphological types. The heating also affects the survival of smaller structures within the disk. Star clusters and associations are more easily disrupted in a dynamically hot environment. Their internal binding must compete with stronger tidal forces and higher relative velocities. This reduces the longevity of clusters and contributes to a smoother, more diffuse stellar distribution. From a broader perspective, Triangulum's disk heating illustrates how environmental effects can reshape galaxies without dramatic mergers. There is no single event to point to, no obvious collision or tidal tail that announces the change. Instead, the galaxy is being transformed by cumulative stress. This is what makes the situation unsettling. The visible structure persists. The galaxy still looks like a spiral, yet beneath that appearance, the kinematic state is shifting towards something else. The disk is no longer the dynamically cold system it once was. If the current trends continue, the next stages are predictable. The disk will continue to thicken. Spiral structure will weaken further. Star formation will become increasingly localized and inefficient. Eventually, the distinction between disk and halo will blur as stellar orbits become more spheroidal. This trajectory does not end in destruction, but in reclassification. Triangulum may survive as a recognizable galaxy, but not as the kind of galaxy it is today. Its identity as a small, well-ordered spiral depends on conditions that are steadily eroding. The question that follows is whether heating alone explains all observed changes, or whether additional processes are accelerating the transformation. The answer lies in how Triangulum's gas supply responds to this dynamical evolution. As the disk heats, gas becomes harder to retain and harder to organize. What happens to that gas may determine whether the galaxy fades quietly or undergoes one final period of activity before settling into decline. Gas is being removed faster than it can be replaced. Galaxies live or die by their gas. Stars are a galaxy's memory, but gas is its future. Without a continuous supply of cold gas, star formation slows, then stops. A galaxy can persist as a collection of aging stars for trillions of years, but once its gas is gone, its evolutionary path is effectively fixed. In Triangulum, multiple lines of evidence indicate that gas is being lost at a rate that internal processes cannot compensate for. For many years, Triangulum was considered relatively gas-rich for its size. Surveys of neutral hydrogen showed an extended gas disk reaching well beyond the visible stellar component. Molecular gas was detected throughout the spiral arms, supporting ongoing star formation. On the surface, there was no sign of imminent depletion. That picture has changed. Recent observations reveal that Triangulum's gas distribution is asymmetric and increasingly fragmented. Large reservoirs remain, but they are unevenly concentrated and truncated along specific directions. The most significant deficits occur on the side of the galaxy facing Andromeda. This directional dependence is not subtle. It is measurable and consistent across multiple datasets. Gas removal does not require direct collision. When a galaxy moves through a diffuse medium, it experiences ram pressure. This pressure acts like a wind, pushing against the galaxy's interstellar medium. If the pressure exceeds the gravitational force holding the gas in place, the gas is stripped away. This process, known as ram pressure stripping, is well documented in galaxy clusters, where galaxies move through hot intra-cluster gas at high velocities. Triangulum does not reside in a cluster, but it does move through Andromeda's extended halo. That halo contains hot, ionized gas spread over hundreds of thousands of light-years. While tenuous by terrestrial standards, it is dense enough to exert force over cosmic timescales. As Triangulum travels through this medium, its outer gas layers are exposed. The effects are strongest where gravitational binding is weakest. In Triangulum, that means the outer disk. Observations show that neutral hydrogen density drops sharply beyond certain radii, particularly along the leading edge of motion. In contrast, the trailing side retains more extended gas structures. This leading trailing asymmetry is a classic signature of ram pressure interaction. The process is gradual but cumulative. Gas is not ripped away all at once. Instead, it is peeled off layer by layer. Diffuse gas goes first. Denser clouds resist longer but eventually become exposed as surrounding material is removed. Over time, the radius at which gas can remain bound shrinks inward. This inward truncation has consequences for star formation. Star formation depends on gas density. As the outer disk loses gas, star formation retreats toward the inner regions. This produces a shrinking star-forming disk, even while the stellar disk remains extended. Triangulum shows signs of exactly this behavior. The gas that is lost does not disappear. It becomes part of Andromeda's circumgalactic medium, mixing with gas expelled by other satellites and by Andromeda itself. From a local group perspective, this is redistribution rather than destruction. From Triangulum's perspective, it is permanent loss. Internal replenishment mechanisms are limited. Galaxies can, in principle, accrete gas from the intergalactic medium. Cold gas filaments feeding galaxies are predicted by cosmological models and observed in some systems. However, Triangulum's environment is hostile to such accretion. Andromeda's halo is hot and massive, shock heating infalling gas and preventing it from cooling efficiently. This means Triangulum cannot easily replace what it loses. Any gas attempting to fall in must first pass through Andromeda's halo, where it is likely heated, ionized, and dispersed. The net flow favors loss over gain. Supernova-driven winds compound the problem. While Triangulum's star formation rate is modest, supernovas still occur regularly. Each explosion injects energy into the surrounding gas, pushing some fraction of it out of the disk. In an isolated galaxy, much of this gas eventually cools and rains back down. In Triangulum's case, the weakened gravitational potential and external pressure make escape more likely. Once gas is lifted out of the disk, it enters an environment where recapture is difficult. The combined effects of reduced dark matter binding, disk heating, and external ram pressure mean that expelled gas often does not return. This turns what would be a recycling process into a one-way flow. Molecular gas, the immediate fuel for star formation, is more tightly bound than neutral hydrogen. It resides deeper in the gravitational well and in denser clouds. For now, much of it remains. But molecular gas depends on shielding from ultraviolet radiation and pressure confinement from surrounding material. As atomic gas is stripped, that shielding weakens. Molecular clouds become more exposed and more susceptible to disruption. This creates a delayed but predictable consequence. Molecular gas survives initial stripping, but becomes harder to maintain over time. Star formation continues in bursts, where conditions remain favorable, but the overall molecular gas reservoir declines as clouds are dispersed or consumed. Observations of carbon monoxide, a tracer of molecular gas, support this picture. Emission is strong in some regions but absent in others where star formation would normally be expected. These gaps align with areas of reduced atomic gas density, indicating a breakdown in the gas phase balance. Another indicator is metallicity gradients. As gas is stripped from the outer disk, the remaining gas becomes more centrally concentrated and more metal-rich. This steepens metallicity gradients across the galaxy. Triangulum shows signs of such steepening, consistent with preferential loss of low metallicity outer gas. Gas loss also alters the pressure balance within the disk. Lower gas surface density reduces the ability of the disk to form new giant molecular clouds. This suppresses large-scale star formation and favors smaller, short-lived star-forming regions. The result is a patchy, inefficient star formation pattern rather than a steady, spiral-driven process. Importantly, gas removal interacts with disk heating. As the stellar disk thickens and gas density drops, the coupling between stars and gas weakens. Spiral density waves lose effectiveness. Gas flows become more chaotic. This accelerates the decline of organized star formation. None of these processes act in isolation. They reinforce one another. Gas stripping reduces star formation. Reduced star formation lowers gravitational cohesion within the disk. Weaker cohesion makes further stripping easier. The system evolves toward a state where gas retention becomes increasingly difficult. From a time-scale perspective, this is not an immediate crisis. Triangulum will not run out of gas tomorrow, or even in the next 100 million years, but when projected forward over several billion years, the trend is clear. Unless conditions change dramatically, gas loss will outpace replenishment. This does not require Triangulum to merge with Andromeda. Even on a wide orbit, continued exposure to the halo environment produces the same outcome. The difference is speed, not direction. A closer orbit accelerates the process. A wider one slows it. But the sign of change remains the same. The long-term implication is a transition from a gas-supported spiral to a gas-poor system. Such galaxies exist throughout the universe. They often retain disks but show little or no star formation. Their stellar populations age and redden. Their spiral structure fades. Triangulum appears to be moving toward that category, not abruptly and not uniformly but steadily. Its current star formation activity masks the underlying trend. The presence of bright young stars gives the impression of vitality. But the reservoir sustaining that activity is shrinking. This realization reframes Triangulum's current state. It is not a stable small spiral in equilibrium. It is a system in the middle of a resource decline, still forming stars, but doing so from a diminishing supply. The question is not whether gas loss will matter, but when its effects will dominate. As gas becomes scarcer, the galaxy's ability to respond to further disturbances diminishes. Any future tidal interaction, any increase in orbital decay, will have a greater impact than it would have in a gas-rich system. The margin for resilience is narrowing. The next step in this progression is not simply less star formation, but structural change. As gas disappears, the disk's remaining stars define the galaxy's morphology. The role of feedback shifts. Internal regulation gives way to passive evolution. Understanding how that transition unfolds requires examining what happens to star formation itself as the gas supply continues to erode. Star formation is becoming episodic and unstable. Star formation in spiral galaxies is often treated as a steady process. Gas flows along spiral arms, clouds collapse, stars ignite, and feedback regulates the pace. Over long periods, the rate fluctuates, but the underlying mechanism remains stable. That assumption no longer holds for Triangulum. The evidence now indicates that star formation there is becoming episodic, uneven, and increasingly decoupled from the galaxy's large-scale structure. This shift is subtle. Triangulum still forms stars. Bright young clusters and emission regions remain visible across the disk. But when examined in detail, the spatial and temporal patterns of star formation no longer resemble those of a self-regulating spiral galaxy. Instead of continuous activity shaped by global dynamics, star formation appears concentrated into bursts triggered by localized conditions. One of the clearest indicators is spatial clustering. In a stable disk, star-forming regions trace spiral arms with relatively uniform spacing. Gas compression from density waves produces predictable patterns. In Triangulum, this coherence is breaking down. Star-forming regions are clustered irregularly, with large gaps between active zones and little correspondence to the underlying spiral geometry. Infrared observations show that many star-forming regions are embedded deeply in dust, indicating rapid, intense bursts rather than prolonged, moderate activity. These regions light up strongly and then fade, leaving behind young stellar populations but little residual gas. This behavior is consistent with short-lived star formation episodes rather than sustained production. Timing adds another layer. Age dating of stellar populations across the disk reveals a patchwork history. Some regions experienced significant star formation within the last few tens of millions of years, while neighboring regions show little activity over the same period. The lack of synchronization suggests that star formation is no longer governed by a common clock set by disk rotation or spiral wave passage. This episodic behavior is a natural outcome of the conditions already described. As gas becomes unevenly distributed and the disk heats dynamically, the mechanisms that once organized star formation weaken. Gas clouds are no longer shepherded smoothly into spiral arms. Instead, they evolve largely in isolation, responding to local pressure fluctuations, turbulence, and external perturbations. The role of turbulence is critical. Elevated turbulence increases internal support within gas clouds, making them more resistant to collapse. At the same time, turbulence can create dense filaments and knots through random compression. The result is a threshold effect. Most of the disk remains quiescent, while a few regions cross the density threshold required for collapse and ignite rapidly. This produces star formation that is intense but inefficient. Large amounts of gas may be present overall, but only a small fraction participates in star formation at any given time. When it does, feedback is strong. Massive stars form, emit radiation, drive winds, and explode as supernovae. These events quickly disrupt the surrounding cloud, halting further star formation locally. In a more stable galaxy, disrupted clouds are replaced by fresh inflows of gas along spiral arms. In Triangulum, that replacement is limited. Once a region burns through its dense gas, it often remains inactive for extended periods. This creates a mosaic of activity rather than a continuous pattern. External influence further destabilizes the process. Tidal forces from Andromeda do not compress the disk uniformly. They introduce directional stress that can compress gas in some regions while stretching it in others. This selective triggering enhances episodic behavior. Star formation lights up where conditions briefly align and shuts down elsewhere. There is also evidence that some recent star formation events coincide with orbital phases. Regions of elevated activity align with areas where simulations predict increased tidal interaction during past close approaches. While the timing is uncertain, the correspondence supports the idea that external forcing is intermittently driving star formation, rather than the galaxy's internal dynamics alone. Chemical signatures reinforce this interpretation. Young star clusters in Triangulum show variations in metallicity that are larger than expected across small spatial scales. In a steady system, mixing smooths these differences. Episodic star formation preserves local chemical conditions, locking them into stars before they can homogenize with the surrounding medium. This patchy chemical record suggests that gas clouds are forming stars before significant mixing occurs. That implies short formation timescales and limited large-scale gas flows. Both are consistent with a disk that has lost much of its ability to organize material coherently. The consequences extend to the stellar population as a whole. Over time, episodic star formation produces a broader age distribution within the disk. Instead of smooth gradients, there are sharp transitions between populations. This complicates the disk's evolution and makes it more susceptible to heating and thickening as stars of different ages and kinematic properties mix. Episodic star formation also changes feedback efficiency. In steady regimes, feedback regulates star formation by maintaining pressure balance. In bursty regimes, feedback overshoots. Strong bursts expel or heat gas beyond what is needed for regulation, contributing to net gas loss. This accelerates the decline in star-forming capacity. Importantly, This is not unique to Triangulum. Similar patterns are observed in satellite galaxies and in spirals transitioning toward quiescence. What makes Triangulum notable is that it is still relatively massive and retains a spiral structure. It represents an intermediate stage that is rarely observed so clearly. From a theoretical standpoint, this stage is unstable. Episodic star formation is not a long-term equilibrium state. It tends to evolve toward one of two outcomes. Either gas inflow increases and restores steady star formation, or gas loss continues and star formation declines further. Given Triangulum's environment, the latter appears more likely. The loss of steady star formation has structural implications. Young stars contribute disproportionately to disk brightness and spiral contrast. As bursts become less frequent and more localized, the visual prominence of the spiral arms fades. The disk appears smoother, older, and less defined, even before star formation fully shuts down. This transition can occur without a dramatic event. There is no single burst that marks the end. Instead, the intervals between bursts lengthen. Active regions become rarer. The galaxy still forms stars, but the process no longer defines its character. There is also a feedback loop with disk heating. As star formation becomes episodic, young stars inject energy into localized regions, increasing velocity dispersion locally. Without global regulation, this energy contributes to further disk heating. The hotter disk then suppresses future star formation, reinforcing the cycle. Another factor is cloud lifetime. In stable disks, molecular clouds can persist for tens of millions of years, forming multiple generations of stars. In Triangulum, cloud lifetimes appear shorter. Rapid disruption limits star formation efficiency and favors bursts over sustained activity. The cumulative effect is a gradual decoupling between gas presence and star formation. Gas remains, but it is increasingly inert. It does not readily collapse into stars except under specific transient conditions. This marks a shift from a star-forming spiral to a gas-rich but inefficient system. From an evolutionary perspective, this is a critical transition. Once star formation becomes episodic and inefficient, recovery becomes difficult. Restoring steady star formation would require reorganizing the disk, replenishing gas, and cooling stellar motions. None of these processes are readily available to Triangulum. The galaxy's future stellar population will reflect this history. Instead of a smooth age distribution, it will show imprints of bursts and lulls. These imprints persist for billions of years, long after the triggering conditions have passed. In this way, the current instability will shape Triangulum's appearance far into the future. This instability also affects how Triangulum interacts with Andromeda. A galaxy with steady star formation can respond to tidal stress by redistributing gas and forming new stars. A galaxy with episodic star formation lacks that flexibility. It absorbs stress as heat and loss rather than renewal. Taken together, the evidence indicates that Triangulum is no longer self-regulating. Star formation, once a stabilizing process, is becoming a symptom of instability. Each burst marks a temporary alignment of conditions rather than a sustainable mode of operation. The next stage to consider is what happens when episodic star formation declines further. When bursts become rarer and weaker, feedback changes character, and the galaxy begins to age visibly. Understanding that transition requires examining how Triangulum's stellar populations are already shifting toward older, redder distributions, and what that implies for its long-term identity within the local group. The stellar population is aging faster than expected. Galaxies carry their histories in their stars. Every generation leaves behind a measurable imprint in color, composition, motion, and spatial distribution. By examining stellar populations, astronomers can reconstruct not only what a galaxy looks like now, but how it has behaved over billions of years. In Triangulum, that reconstruction is revealing a shift that is difficult to ignore. The galaxy's stellar population is aging more rapidly than models predict for a small, actively star-forming spiral. At first glance, this seems contradictory. Triangulum still forms stars. Blue stars are visible in its spiral arms. Emission regions mark sites of recent activity, but stellar population analysis does not measure presence alone. It measures balance. In Triangulum, the balance between young and old stars is shifting toward older populations faster than expected. This conclusion comes from color magnitude diagrams constructed using deep multi-wavelength observations. These diagrams plot stars by brightness and color, allowing astronomers to determine their ages and evolutionary stages. In a galaxy with steady star formation, these diagrams show a continuous distribution of stellar ages. In Triangulum, that continuity is breaking down. Large portions of the disk are dominated by intermediate age and old stars, with fewer young stars than expected given the galaxy's remaining gas content. The young stars that do exist are concentrated in isolated regions rather than distributed broadly. This produces a disk that looks active in places but increasingly quiescent overall. The aging trend is most pronounced in the outer disk. These regions once hosted extended star formation supported by abundant gas. Now, stellar populations there are skewed toward older ages, with few signs of recent formation. This is consistent with the inward retreat of star formation driven by gas loss and disk heating. The inner disk tells a more complex story. Star formation persists there, but even in these regions, the fraction of very young stars relative to the total stellar mass is declining. Bursts still occur, but they contribute less to the long-term population balance than they did in the past. The result is a galaxy that appears youthful in snapshots, but is aging steadily when averaged over time. Metallicity patterns reinforce this interpretation. Younger stars in Triangulum tend to be metal-rich, reflecting repeated cycles of star formation and enrichment. However, the overall metallicity distribution is becoming dominated by older, moderately enriched stars, rather than by a growing cohort of newly formed ones. This indicates that enrichment is slowing, a sign of declining star formation efficiency. Another indicator is the luminosity function of massive stars. Massive stars are short-lived. Their presence signals very recent star formation. Surveys show that these stars are present, but underrepresented relative to what would be expected if current star formation rates had been sustained over long periods. This implies that recent activity is not representative of the galaxy's longer-term behavior. The aging process is also reflected in the disk's color gradients. Triangulum's disk is reddening from the outside inward. Outer regions are dominated by redder stars, while bluer populations are increasingly confined to the inner disk and to isolated pockets. This gradient steepening is characteristic of galaxies transitioning away from widespread star formation. Stellar kinematics provide additional context. Older stars in Triangulum exhibit higher velocity dispersion than younger ones, as expected. But the dispersion of intermediate age stars is also elevated. This suggests that heating processes have been acting not just recently, but over a significant fraction of the galaxy's lifetime. The cumulative effect is a population that is dynamically older than its chronological age would suggest. This dynamical aging matters because it affects future evolution. Older, dynamically hot stellar populations do not easily support disk structures like spiral arms. As these populations come to dominate the mass budget, the disk's ability to organize gas and trigger star formation diminishes further. The mismatch between remaining gas and declining stellar youth is particularly telling. In isolation, gas-rich galaxies typically maintain a relatively young stellar population. Triangulum breaks this pattern. Its gas is present, but increasingly ineffective at producing stars. This decoupling accelerates stellar aging even before gas is fully depleted. Comparisons with similar mass isolated spirals highlight the anomaly. Galaxies of comparable size and gas content in low-density environments show more balanced age distributions and more extended star formation histories. Triangulum's accelerated aging appears linked to environment, rather than intrinsic properties. The environment's role becomes clearer when considering timescales. Stellar aging reflects conditions integrated over hundreds of millions to billions of years. The observed trends therefore imply that Triangulum has been under environmental stress for a long time. The processes described in earlier chapters are not recent developments. They have been shaping the galaxy's evolution for much of its recent history. This aging does not imply imminent extinction. Many galaxies exist for trillions of years dominated by old stars, but it does indicate a change in evolutionary direction. Instead of replenishing its stellar population at a steady rate, Triangulum is increasingly living off its past. The spatial imprint of this shift will persist. Even if star formation were somehow revitalized in the future, the existing age structure would remain. Old and intermediate age stars do not disappear. They define the mass distribution and influence dynamics long after star formation conditions change. There is also a feedback relationship with gas dynamics. As the stellar population ages and massive stars become rarer, feedback changes character. Fewer supernovae occur per unit mass of stars formed. This reduces one source of turbulence, but also reduces the recycling of gas and the triggering of new star formation. The system becomes more passive. This passivity feeds into disk heating and gas loss. Without continuous injection of young stars and associated feedback, the disk becomes less resilient. It responds to external perturbations by heating rather than reorganizing. This further suppresses star formation and accelerates aging. The net effect is a gradual shift toward a redder, more quiescent galaxy. Triangulum is not yet a red galaxy in the classical sense. Its integrated color still reflects ongoing star formation. But the trend is unmistakable when examined in detail. Importantly, stellar aging is one of the hardest processes to reverse. Gas can be reaccreted under the right conditions. Orbits can be altered by mergers, but the age distribution of stars only moves in one direction. Once a galaxy's stellar population skews old, that imprint defines its long-term identity. This raises the question of classification. Triangulum is currently classified as a late-type spiral, but morphological classification lags physical reality. Galaxies often retain spiral features long after their star formation histories have begun to resemble those of earlier types. Triangulum may be entering that transitional phase. In such phases, appearances can be misleading. A galaxy may look like a spiral, but behave like a system in decline. The difference only becomes apparent through detailed population analysis. That analysis now suggests that Triangulum's most active period may already be behind it. The broader implication is that Triangulum's future will be defined less by what it does next, and more by what it has already done. Its current stars, formed during earlier, more stable epochs, will dominate its light and mass for the rest of its existence. The question that follows is not whether Triangulum will continue to age, but how its aging stellar population will interact with its changing structure. As the disk heats, gas thins, and star formation becomes rarer, the galaxy's morphology itself may begin to change. Understanding that transformation requires examining how the disk responds structurally when young stars no longer provide cohesion and contrast. And that response is already beginning to take shape. Spiral structure is losing coherence. Spiral structure is not a permanent feature of disk galaxies. It is a dynamic pattern sustained by ordered motion, gravitational balance, and a continuous exchange between stars and gas. When those conditions weaken, spiral arms do not vanish abruptly. They lose coherence. Contrast fades. Geometry fragments. What remains is a disk that still rotates, but no longer organizes itself into long-lived, well-defined patterns. In Triangulum, this loss of coherence is already underway. The galaxy retains visible spiral arms, but closer inspection shows that these arms lack the continuity and symmetry expected in a dynamically cold, self-regulating system. They appear uneven in strength, broken into segments, and inconsistent in pitch angle across the disk. These features are not cosmetic. They are structural indicators of an underlying dynamical shift. Classic spiral arms rely on density wave theory or related mechanisms, in which stars and gas respond collectively to a rotating gravitational pattern. For this to work, stellar orbits must remain relatively circular, and gas must be able to flow smoothly through the disk. Disk heating disrupts both requirements. As stellar velocity dispersion increases, stars respond less coherently to density perturbations. The wave loses support. Triangulum's disk heating, discussed previously, directly undermines the conditions required for sustained spiral structure. Stars with elevated random motions spend less time near the midplane and less time reinforcing spiral density enhancements. Instead of amplifying the wave, they wash it out. Over time, this reduces arm contrast and continuity. Gas dynamics compound the problem. Spiral arms depend on gas compression to remain visible and effective. As gas density declines and becomes unevenly distributed, the arms lose one of their primary traces. Star formation no longer highlights the spiral pattern consistently. Some arm segments light up briefly during bursts, while others remain dark. Infrared observations show this clearly. Dust emission, which traces dense gas and recent star formation, outlines spiral structure unevenly. Instead of continuous arcs, the arms appear as disconnected segments. In some regions, the pattern is barely discernible at all. This is not an artifact of dust obscuration or viewing angle. It reflects real structural discontinuity. The loss of coherence is also evident in kinematic maps. Gas and stars in different parts of the disk no longer share a common spiral-aligned flow. Velocity residuals vary irregularly along the arms, indicating that the gravitational perturbation driving the spiral pattern is weak or transient. In a strong spiral, these residuals would align systematically. This behavior aligns with simulations of galaxies undergoing tidal heating and gas loss. In such systems, spiral structure transitions from a global mode to a transient, locally driven phenomenon. Arms appear, dissolve and reappear in different locations, driven by stochastic instabilities rather than by a stable pattern speed. Triangulum appears to be entering this regime. Its spiral arms are no longer long-lived features rotating with a consistent pattern speed. Instead, they behave more like temporary alignments of star-forming regions and gas over-densities. This makes the spiral pattern less predictive and less influential in shaping the galaxy's evolution. The weakening of spiral structure has immediate consequences for star formation. Spiral arms are efficient at funneling gas, triggering collapse and regulating feedback. When arms lose coherence, gas flows become disorganized. Star formation becomes localized and inefficient, reinforcing the episodic behavior already observed. There is also a feedback relationship with disk heating. Weak spiral arms are less effective at redistributing angular momentum. This allows random motions to grow unchecked. As the disk heats further, spiral structure weakens even more. The system moves away from a spiral-supported equilibrium. Another factor is the diminishing role of self-gravity in the disk. As gas mass declines and dark matter support weakens, the disk's ability to sustain collective gravitational modes decreases. Spiral arms require a disk that is massive enough, relative to its halo, to influence its own dynamics. Triangulum's disk appears to be losing that influence. This shift changes how the galaxy responds to external perturbations. In a galaxy with strong spiral structure, tidal forces can reinforce or distort existing arms. In a galaxy with weak structure, the same forces produce irregular distortions rather than coherent features. Triangulum's asymmetries increasingly fall into the latter category. The geometry of the arms also reflects this change. Pitch angles vary significantly across the disk, suggesting that there is no single pattern governing their shape. In stable spirals, pitch angle correlates with rotation and mass distribution. Large variations indicate that local conditions dominate. The fading of spiral coherence is not unique to Triangulum. Many galaxies transitioning toward quiescence show similar behavior. What makes Triangulum significant is that this process is occurring without a major merger or internal bar-driven transformation. It is being driven by cumulative environmental effects. Bars deserve mention in this context. Bars can either strengthen or replace spiral structure by redistributing angular momentum. Triangulum lacks a strong central bar. This absence removes a potential stabilizing mechanism. Without a bar to reorganize the disk, the weakening spiral pattern has no obvious successor. The loss of spiral coherence also affects how the galaxy appears over time. As young stars become rarer and more localized, the visual prominence of the arms declines. The disk appears smoother and more featureless, even before star formation ceases entirely. This visual evolution can precede significant changes in global star formation rate. This is an important distinction. Morphological change does not wait for star formation to stop. It begins as soon as the structures that organize star formation weaken. Triangulum's morphology may therefore evolve faster than its star formation metrics alone would suggest. Another subtle consequence involves angular momentum transport. Spiral arms play a key role in moving angular momentum outward, allowing gas to flow inward and sustain central activity. As arms weaken, this transport becomes inefficient. Gas remains stranded in the disk or is lost, rather than being funneled inward in a regulated way. This inefficiency affects the central regions as well. While Triangulum lacks a prominent bulge, its inner disk still depends on inflows to maintain star formation. As spiral-driven inflow declines, even the inner regions become more vulnerable to gas depletion. The cumulative picture is one of structural erosion rather than collapse. The galaxy is not tearing itself apart. It is losing the patterns that once gave it coherence. Rotation remains. The disk persists. But the organizing framework that once defined its spiral nature is fading. This erosion also changes how Triangulum will respond to future interactions. A galaxy with strong spiral structure can absorb tidal perturbations by redistributing energy through density waves. A galaxy with weak structure absorbs that energy as heat and distortion. This makes future encounters more damaging. From a long-term perspective, the loss of spiral coherence marks a point of no easy return. Restoring global spiral structure would require cooling the disk, replenishing gas, and re-establishing strong self-gravity. Given Triangulum's environment, these conditions are unlikely to be met. The galaxy may retain spiral fragments for billions of years, but their role will be diminished. They will no longer define the galaxy's behavior or regulate its evolution. Instead, they will be remnants of an earlier state, gradually fading as the disk ages and heats. This stage is often overlooked because it lacks drama. There is no single event, no sharp transition. Spiral structure simply becomes less effective over time. But this quiet change has profound implications. Once the disk loses its organizing patterns, many other processes follow. The next of those processes involves how mass is redistributed within the galaxy. As spiral arms weaken and angular momentum transport falters, material does not remain evenly distributed. Some regions grow denser, others empty out. This internal rebalancing sets the stage for further structural change, particularly in the central regions, where even small shifts can have lasting effects. The central regions are not compensating. In many galaxies undergoing environmental stress, the central regions act as a stabilizing reserve. As outer disks lose gas and structure, material flows inward, deepening the central potential and sustaining star formation near the core. This inward migration can partially offset losses elsewhere, allowing the galaxy to persist in a compact but active state. In Triangulum, that compensatory process appears weak or absent. Triangulum lacks a prominent central bulge. This has long been considered a defining characteristic of the galaxy and a clue to its quiet evolutionary past. Bulges act as gravitational anchors. They stabilize disks, concentrate gas, and provide resistance against external perturbations. Without one, a galaxy relies more heavily on its disk and dark matter halo to maintain coherence. As both of those supports weaken, the absence of a central stabilizer becomes increasingly consequential. Observations of Triangulum's inner regions show modest gas concentrations and ongoing star formation, but not at a level sufficient to counterbalance losses elsewhere. Gas surface density rises toward the center as expected, but the increase is gradual rather than dramatic. There is no evidence of a strong inflow channeling large amounts of material inward. In galaxies with bars or strong spiral structure, angular momentum transport drives gas toward the center. Triangulum has neither. Its weakening spiral arms are no longer effective at funneling gas inward, and the lack of a bar removes another major pathway for redistribution. As a result, gas remains spread across the disk or is lost altogether, rather than accumulating centrally. Kinematic studies support this conclusion. Gas motions in the inner disk do not show the signatures of sustained inflow. Velocities are consistent with rotation and localized turbulence, but not with large-scale inward streaming. This suggests that whatever gas remains in the disk is largely decoupled from the central regions in terms of long-term supply. Star formation in the center reflects this limitation. While young stars are present, their formation appears episodic rather than continuous. Bursts occur when local conditions allow, but they are not part of a sustained, centrally driven process. The central star formation rate fluctuates rather than maintaining a steady baseline. The scale of the central region matters. Triangulum's inner disk is relatively small compared to those of more massive spirals. This limits the volume available for gas accumulation and star formation. Even if some inflow occurs, it cannot build a dense, stabilizing core comparable to a bulge-dominated galaxy. Another factor is feedback efficiency. In small central regions, feedback from supernovae and stellar winds can have an outsized impact. Energy injected into a limited volume can quickly disrupt gas, halting star formation and expelling material. In Triangulum, this feedback likely prevents gas from settling into a long-lived central reservoir. The metallicity distribution adds further context. Central metallicities are higher than in the outer disk, indicating past enrichment. However, the gradient is not flattening, as would be expected if significant new gas were flowing inward and mixing. Instead, the gradient remains steep, suggesting limited redistribution. This lack of central compensation has structural implications. As the outer disk fades and the spiral pattern weakens, the galaxy does not transition into a compact, centrally concentrated system. Instead, it retains a diffuse disk with declining activity across all radii. The center does not take over as the dominant engine of evolution. In many environmental transformation scenarios, galaxies evolve from late-type spirals into lenticular systems, characterized by prominent bulges and smooth disks. Triangulum does not fit neatly into this pathway. Its bulge remains small, and its disk is becoming dynamically hot without central consolidation. This places it on a less common evolutionary track. The dark matter context again plays a role. A robust dark matter halo can support central gas accumulation by deepening the potential well. As Triangulum's halo weakens or becomes distorted, the gravitational incentive for gas to sink inward diminishes. Gas that might otherwise migrate centrally instead remains marginally bound or is lost. The absence of central compensation also affects resilience. Central regions often help galaxies survive further perturbations. They provide a dense core that can absorb tidal energy without severe disruption. Triangulum's center lacks that buffering capacity. As a result, future interactions, even mild ones, will have more uniform impact across the disk rather than being damped centrally. This uniform vulnerability aligns with observed patterns of disturbance. Asymmetries and heating are not confined to the outskirts. They extend inward, though with reduced amplitude. This suggests that the galaxy has no protected zone where structure and activity remain insulated from environmental effects. From a long-term perspective, this changes the end state toward which Triangulum is evolving. Instead of becoming a compact, bulge-dominated system, With residual star formation, it is more likely to become a diffuse, gas-poor disk with little central concentration. Such systems exist, but they are typically found in environments where gradual stripping dominates over mergers. This outcome also affects observational classification. A galaxy with weak spiral structure, low star formation, and no strong bulge challenges traditional categories. It may be labeled as a late-type spiral long after its physical processes resemble those of earlier or transitional types. The lack of central compensation also means that any recovery scenario becomes less plausible. Even if external conditions were to become more favorable, there is no established central reservoir from which renewed growth could proceed. Rebuilding from the inside out would require substantial new gas accretion, which the environment does not support. This reinforces the theme that Triangulum's transformation is not being redirected or stabilized internally. Each weakening component is not offset by strengthening elsewhere. Instead, the galaxy is thinning uniformly in terms of functional structure, even as its visible form persists. The implications extend to mass distribution. As central mass does not increase, the gravitational profile of the galaxy becomes flatter. This further reduces binding in the outer disk and contributes to ongoing gas and stellar loss. The system becomes progressively less able to hold onto its material at all radii. This interconnected decline illustrates how galactic evolution can proceed without a single dominant mechanism. No one process is catastrophic on its own. Disk heating, gas loss, halo erosion, and weak central inflow each contribute incrementally. Together, they produce a trajectory that is difficult to reverse. Triangulum's central regions therefore serve as a negative indicator, not because they are failing dramatically, but because they are failing quietly to compensate. Their relative inactivity is itself evidence that the galaxy's internal regulatory mechanisms are no longer functioning as they once did. The next question is how long this intermediate state can persist. A galaxy with weakening spiral structure, episodic star formation, and no central consolidation can remain recognizable for a long time. But its role within the local group changes. It becomes less an active participant and more a passive component shaped by its surroundings. Understanding that role requires shifting focus from internal structure to environmental context. If Triangulum is no longer self-regulating, then its future is increasingly dictated by the larger gravitational systems around it. The consequences of that shift become clearer when examining how Triangulum interacts, not just with Andromeda, but with the broader local group environment that envelops both. The local group environment is closing in. Triangulum does not evolve in isolation. Its fate is tied not only to Andromeda, but to the broader gravitational and gaseous environment of the local group itself. That environment is not static. It is contracting, reorganizing, and becoming increasingly dominated by the mutual approach of its two largest members. As this happens, the space in which a small spiral like Triangulum can behave independently continues to shrink. The local group is often described as a loose collection of galaxies separated by vast distances. That description is misleading. While distances are large in human terms, gravitational influence extends far beyond visible disks. The local group is bound together by overlapping dark matter halos, diffuse gas, and long-range tidal forces. Triangulum sits deep within this interconnected structure. The most important change underway is the gradual convergence of the Milky Way and Andromeda. Their relative motion is well measured and unambiguous. They are moving toward each other on a timescale of several billion years. As they do, their dark matter halos increasingly overlap, forming a shared gravitational envelope that reshapes the local group's internal dynamics. Triangulum lies within this evolving overlap region. This matters because overlapping halos do not simply add their effects linearly. They create a complex, time-dependent gravitational field with gradients that shift as the major galaxies move. For a smaller system like Triangulum, This means that the background gravitational potential is changing, even if its own orbit were perfectly stable, which it is not. This changing potential affects orbital predictability. In a static environment, a satellite galaxy might settle into a long-lived orbit. In a dynamic environment, orbital parameters drift, small perturbations grow. Paths that once avoided close encounters can evolve into ones that do not. Triangulum's trajectory must therefore be understood as evolving within a moving gravitational landscape. The local group environment also includes diffuse gas, much of it hot and ionized. This gas is distributed unevenly, concentrated around massive halos and along filaments connecting them. As Andromeda and the Milky Way draw closer, these gas reservoirs are compressed, heated, and redistributed. The density of the circumgalactic medium in which Triangulum moves is therefore likely increasing over time. An increase in ambient gas density has direct consequences: ram pressure scales with both velocity and medium density. Even modest increases in density can significantly enhance stripping efficiency over long timescales. This means that gas loss processes affecting Triangulum today may intensify in the future, even without changes in its intrinsic properties. The local group also contains numerous smaller galaxies and dark subhalos. While individually insignificant compared to Andromeda, their collective gravitational influence contributes to background noise in the system. Close passages with these substructures can inject additional energy into Triangulum's disk and halo, further heating and destabilizing them. Such encounters do not need to be direct collisions. Passing within tens of thousands of light-years is sufficient to perturb a small galaxy's outer halo. Over billions of years, repeated weak interactions accumulate. This process, often called harassment in denser environments, operates at a lower intensity in the local group, but over longer timescales. Triangulum's position makes it particularly vulnerable to these cumulative effects. It occupies a region where gravitational gradients from Andromeda, the Milky Way, and the shared halo overlap. This is not a quiet zone. It is a region of slow but persistent dynamical activity. Another factor is tidal field orientation. The combined gravitational field of the local group produces tidal stresses that vary in direction over time. This variability prevents Triangulum from settling into a stable orientation or shape. Disk warps and asymmetries are maintained rather than damped, contributing to long-term structural disorder. The local group environment also constrains future gas accretion. Even if Triangulum were to encounter diffuse gas clouds, their thermal state is unfavorable. Most gas in the local group is hot, ionized, and pressure-supported. Cooling times are long, especially in regions influenced by massive halos. This effectively cuts off external fuel supplies. In cosmological terms, Triangulum is living in a closed system. The era of significant cold gas accretion is over for galaxies in environments like the local group. Growth through fresh inflow has largely ceased. Evolution now proceeds through redistribution and loss rather than replenishment. This environmental closure marks a transition point. Early in a galaxy's life, its fate is shaped by what it can gather from its surroundings. Later, it is shaped by what it can hold. Triangulum appears to be well into the latter phase. Its environment no longer offers resources, only constraints. The combined effect of these constraints is subtle but decisive. Triangulum's future evolution becomes increasingly deterministic. There are fewer viable pathways. Major rejuvenation scenarios require conditions that no longer exist. The range of possible outcomes narrows toward gradual fading or eventual absorption. Importantly, none of this requires a dramatic event. The local group does not need to undergo a sudden collapse. The Milky Way and Andromeda do not need to collide tomorrow. The slow tightening of their gravitational embrace is enough to reshape the environment in which Triangulum exists. This tightening also affects timescales. Processes that once took tens of billions of years can accelerate to a few billion. Orbital decay speeds up, gas stripping intensifies, disk heating becomes more efficient. What once appeared stable on cosmic timescales begins to look transitional. The local group environment therefore acts as a background driver, amplifying every vulnerability already present within Triangulum. A weakening halo becomes more exposed, a heated disk becomes more responsive to tides, a shrinking gas reservoir becomes harder to protect. None of these processes operate independently of environment. This perspective changes how Triangulum should be interpreted observationally. It is tempting to view it as a standalone object whose current properties reflect internal evolution. In reality, many of those properties are responses to external pressure. Triangulum is not merely aging, it is being aged by its surroundings. This has implications for how similar galaxies are interpreted elsewhere. Small spirals near larger hosts may appear healthy in snapshots, but be well along a path of environmental transformation. Triangulum provides a nearby example of how that path unfolds in slow motion. The closing in of the local group environment also raises questions about timing. How long can Triangulum remain recognizable as a spiral before environmental effects dominate its appearance? The answer depends not on a single threshold, but on cumulative change. Each billion years removes a little more flexibility. As the environment tightens further, Triangulum's options diminish. It cannot escape the local group. It cannot easily acquire new gas. It cannot stabilize itself internally. Its evolution becomes increasingly reactive rather than self-directed. The next stage of analysis must therefore confront long-term outcomes. Given the environmental constraints now in place, what are the realistic end states for Triangulum? Will it survive as a distinct but quiescent system, or will it eventually be subsumed into a larger structure? Answering that requires projecting current trends forward rather than looking backward and examining how similar systems have evolved under comparable conditions. The path toward long-term quiescence is taking shape. When galaxies stop forming stars, they do not switch off abruptly. The transition from an active, star-forming system to a quiescent one unfolds through intermediate stages that can last billions of years. Triangulum is entering one of those stages now. The processes described so far do not yet define a dead galaxy. They define a galaxy whose future activity is increasingly constrained, whose remaining pathways narrow with time. Quiescence, in a physical sense, means the absence of sustained star formation. It does not require a galaxy to lose all gas or all structure. It requires only that conditions no longer support the regular collapse of gas into new stars. In Triangulum, those conditions are being eroded from multiple directions at once. The first constraint is supply. Gas loss continues at the outskirts, and replenishment from outside the local group is effectively shut down. The remaining gas is increasingly centralized, turbulent, and unevenly distributed. This alone does not end star formation, but it reduces its reliability. Star formation becomes dependent on rare alignments of local conditions rather than on global disk processes. The second constraint is organization. Spiral structure, once the primary organizing mechanism for star formation, is losing coherence. Without long-lived density patterns, gas is not guided into predictable star-forming zones. Instead, it drifts, fragments, and occasionally collapses in isolation. This lowers the overall efficiency of converting gas into stars. The third constraint is dynamics. Disk heating raises the velocity dispersion of both stars and gas. Gas clouds moving at higher relative speeds are less likely to merge and collapse. Even when dense regions form, they are more easily disrupted by feedback. The disk becomes a hostile environment for sustained star formation. The fourth constraint is feedback imbalance. In steady star-forming galaxies, feedback regulates activity by maintaining equilibrium. In episodic systems like Triangulum, feedback overshoots. Bursts of star formation inject energy into a medium that is already marginally stable. Instead of fine-tuning collapse, feedback accelerates gas dispersal and loss. These constraints reinforce one another. Reduced organization amplifies the impact of heating. Heating magnifies the effects of feedback. Feedback enhances gas loss. Gas loss weakens spiral structure further. The system moves toward a state where star formation is possible, but not persistent. This is the hallmark of a transition toward quiescence. The galaxy still forms stars, but those stars no longer define its long-term trajectory. Each new generation contributes less to the total stellar mass and has less influence on structure and dynamics. The galaxy's evolution becomes dominated by aging rather than renewal. Observationally, this transition is difficult to capture because it does not produce dramatic signatures. Star formation rates decline slowly, colors redden gradually, morphology changes subtly. Without long-term data, the shift can be mistaken for ordinary fluctuation. But when integrated over billions of years, the trend is unmistakable. Triangulum's current star formation rate, while non-zero, is already lower than what would be expected if its gas content were being used efficiently. This inefficiency is a warning sign. Galaxies do not become quiescent because gas vanishes overnight. They become quiescent because gas stops behaving like fuel. Another indicator lies in the spatial retreat of activity. Star formation in Triangulum is increasingly confined to the inner disk and isolated pockets. The outer disk, once a significant contributor, is fading. This inside-out quenching pattern is common in galaxies, transitioning toward quiescence, particularly in environments where stripping and heating dominate. The lack of central consolidation complicates this picture. In many galaxies, quenching proceeds alongside bulge growth, producing a compact red core surrounded by a faded disk. Triangulum lacks a mechanism for significant bulge formation. As a result, quiescence is likely to emerge without a corresponding increase in central density. This leads to an important distinction. Triangulum is not evolving toward the typical quiescent galaxy found in dense clusters. It is evolving toward a low-density, gas-poor, dynamically warm system that retains a disk-like shape but lacks internal activity. Such systems exist, but they are underrepresented in classical classification schemes. The timescale of this transition matters. If gas loss and heating continue at current rates, Triangulum could cross the threshold into effective quiescence within a few billion years. That threshold does not mark the end of all star formation, but the point at which star formation becomes too weak and too rare to influence the galaxy's structure or evolution. Beyond that point, aging accelerates perceptually. With few new stars to replenish blue light, the galaxy's integrated color shifts steadily redward. Spiral features fade as young stars die out. The disk becomes smoother and more uniform in appearance, even if it remains rotationally supported. This does not imply structural collapse. The galaxy will not suddenly transform into an elliptical. Its angular momentum is too high, and no major merger is imminent. Instead, it will persist as a faint, diffuse disk dominated by older stars, orbiting within the gravitational influence of Andromeda. From a dynamical perspective, such a system is stable but inert. It continues to orbit, rotate, and evolve slowly through internal relaxation and external tides. But its role as a site of active star formation ends. It becomes a fossil of earlier epochs. The transition toward quiescence also changes how Triangulum interacts with its environment. A star-forming galaxy can respond to tidal stress by forming new stars and redistributing gas. A quiescent or near-quiescent galaxy absorbs stress as heat and mass loss. This makes it more susceptible to further stripping and erosion. This susceptibility feeds forward into orbital evolution. As mass decreases, dynamical friction changes character. The galaxy's response to Andromeda's halo evolves. Its orbit may decay further, or it may become more easily perturbed by future interactions within the local group. The key point is that quiescence is not an endpoint in itself. It is a phase that alters everything that follows. Once a galaxy becomes quiescent, its remaining evolution is dominated by gravitational processes, rather than by internal regulation. For Triangulum, That means its fate becomes even more tightly coupled to Andromeda and the local group environment. From a broader astrophysical perspective, this stage is critical. It represents the point at which a galaxy's individuality begins to fade. It still exists as a distinct object, but its internal processes no longer set its destiny. External forces take precedence. Triangulum's current state suggests that this handoff is already underway. Internal star formation still occurs, but it no longer governs the galaxy's future. The trajectory is being set by environment, orbit, and mass loss. This does not make Triangulum uninteresting. On the contrary, it makes it unusually valuable as an observational case. Few galaxies of this mass and morphology can be studied in such detail while undergoing this transition. Triangulum offers a rare window into how quiescence emerges without a violent trigger. The question that remains is how this trajectory resolves over longer timescales. Quiescence can persist indefinitely, or it can be followed by absorption into a larger system. Whether Triangulum remains a long-lived, inert companion or is eventually subsumed depends on how its mass, orbit, and environment evolve together. Answering that requires looking beyond the near future and considering the ultimate outcomes permitted by the local group's dynamics. The processes shaping Triangulum now are slow, but they are directional. Projected far enough forward, they converge on a small number of plausible end states, each defined less by internal transformation than by external integration into a larger cosmic structure. Absorption without collision becomes the dominant scenario. When galaxies are absorbed by larger systems, the process is often imagined as violent and unmistakable. Tidal tails stretch across space, stellar streams arc outward, and dense cores plunge toward one another. That imagery reflects major mergers. What Triangulum appears to be facing is something very different. Its likely future is absorption without collision, a slow integration driven by gravity rather than impact. Absorption without collision occurs when a galaxy loses its independence not through a direct merger of stellar disks, but through gradual mass loss, orbital decay, and halo assimilation. The visible structure can persist for a long time, even as the galaxy becomes dynamically subordinate. In such cases, the decisive changes happen first in the dark matter halo, then in gas, and only much later in the stellar component. For Triangulum, this pathway aligns with every trend already observed. Its dark matter halo shows signs of erosion and distortion. Its gas is being stripped and dispersed. Its orbit is decaying rather than stabilizing. None of these processes require a close passage through Andromeda's stellar disk. They require only prolonged residence within Andromeda's gravitational domain. As Triangulum continues to lose mass, its gravitational influence shrinks. This changes the nature of its orbit. A less massive object experiences weaker self-gravity and stronger relative dynamical friction. Over time, this leads to further orbital decay, even if the absolute strength of friction decreases slightly as mass is lost. The orbit does not settle into equilibrium, it continues to evolve. At some point, the distinction between Triangulum's halo and Andromeda's halo becomes largely semantic. Dark matter particles originally bound to Triangulum are redistributed into Andromeda's extended halo. They retain memory of their origin only statistically, through subtle phase space signatures. Dynamically, they become part of the larger system. This transition has already begun. Simulations of satellite evolution in similar environments show that halo stripping precedes all other forms of assimilation. By the time visible disruption becomes obvious, the satellite's dark matter identity has long since been diluted. Triangulum's current halo anomalies suggest it is well into this phase. Gas follows a similar trajectory. Stripped gas does not fall directly into Andromeda's disk. Instead, it joins the circumgalactic medium, where it mixes with gas from other sources. Over time, some fraction may cool and accrete onto Andromeda, but the process is indirect and slow. From Triangulum's perspective, this gas is permanently lost. As gas loss continues, the galaxy's baryonic mass declines. Star formation weakens further. Feedback diminishes. The remaining stars increasingly behave as collisionless tracers, responding primarily to the gravitational field of Andromeda rather than to Triangulum's internal potential. This is the defining characteristic of absorption without collision. The galaxy does not disintegrate into streams immediately. Instead, it becomes dynamically transparent. Its stars orbit within a larger potential, gradually losing coherence as a distinct system. The process resembles evaporation more than destruction. In this regime, Triangulum's stellar disk may persist for billions of years, but its boundaries blur. Stellar orbits become more eccentric and inclined. The disk thickens further. The distinction between disk and halo stars weakens. Eventually, what remains is a diffuse stellar overdensity embedded within Andromeda's halo. The absence of dramatic tidal features does not contradict this outcome. Tidal tails form most readily during close impulsive encounters. Absorption without collision involves long-range adiabatic processes. Energy is transferred slowly, allowing the stellar system to adjust without producing sharp features. This explains why Triangulum still appears relatively intact. The forces acting on it are persistent but gentle on short timescales. They reshape phase space rather than tearing matter away abruptly. To an observer watching over millions of years, little seems to change. Over billions, everything does. The local group environment reinforces this pathway. As the Milky Way and Andromeda continue to approach each other, the shared gravitational field deepens. Smaller systems embedded within that field become increasingly subordinate. There is no stable niche for a low-mass spiral to maintain full independence indefinitely. Absorption without collision also explains why alternative outcomes are becoming less likely. A rejuvenation scenario would require significant new gas accretion and halo regrowth, neither of which is supported by the environment. A dramatic merger would require a close encounter that current orbital models do not favor. Gradual integration remains the most consistent trajectory. From a classification standpoint, this outcome challenges traditional categories. Triangulum may retain a recognizable form long after it has ceased to function as an independent galaxy. Its identity becomes historical rather than dynamical. It is a galaxy by appearance, but not by autonomy. This distinction matters for interpretation. Astronomers often classify galaxies based on morphology and current star formation. Absorption without collision decouples these indicators from underlying fate. A galaxy can look stable even as it is being dismantled dynamically. There is precedent for this. Observations of large galaxy halos reveal stellar substructures that are remnants of absorbed systems. Many of these remnants show little evidence of having undergone violent disruption. They are diffuse, kinematically warm populations spread across the halo. Their progenitors likely followed paths similar to what Triangulum now appears to be on. The timeline for this process is long. Even after losing most of its gas and halo mass, Triangulum's stellar component could persist as a coherent overdensity for several billion years. Complete phase mixing takes time. During this period, the galaxy remains identifiable, though increasingly altered. This slow disappearance is difficult to reconcile with intuitive notions of galactic evolution. It lacks a defining moment. There is no final plunge, no single epoch to mark the end. Instead, independence fades gradually, until it becomes meaningless to ask where Triangulum ends and Andromeda begins. The implications extend beyond Triangulum. They suggest that many satellite galaxies may already be absorbed in this sense, even if they remain visible. The universe may contain fewer truly independent galaxies than appearances suggest. For Triangulum, absorption without collision is not an event on the horizon. It is a process already in progress. The erosion of its halo, the loss of gas, the instability of its orbit, and the weakening of its internal structure all point in the same direction. The galaxy is being incorporated into a larger system piece by piece. This does not negate the significance of Triangulum as an object of study. On the contrary, it makes it uniquely informative. Observing a galaxy in this phase allows astronomers to test models of long-term satellite evolution that are otherwise accessible only through simulations or fossil remnants. The remaining question is not whether absorption will occur, but how it will manifest observationally as time goes on. Which components will dissolve first? How long will the stellar disk remain recognizable? And how will this process interact with the eventual Milky Way-Andromeda merger? Those questions point toward the final layers of Triangulum's story. Not an ending, but a continuation into a future where its identity becomes increasingly diffuse, shaped less by its own structure and more by the gravitational framework of the local group as a whole.